What's up, guys? Today we'll code something really exciting. We're gonna be creating a tool called Toralizer. It's a command line client for connecting to the Tor privacy network. When you run a CLI command for doing a network call, for example curl, the following thing happens. The connect function is invoked and the program establishes a TCP connection to the remote server, and then the communication begins. But with this tool, you'll be able to put the word Toralize in front of any command which does a network call. Toralize will intercept any calls to the connect function and execute our function instead. The traffic will be redirected to a local proxy server, which is a part of the Tor software. It will connect to the Tor network and then to the destination server, effectively masking your identity and helping you to stay private on the internet. And the best thing is, coding this is easier than you might think. Let's get on with it. Okay guys, welcome to this episode. The first thing we need to do today is we're gonna create our own proxy server client. So this proxies, it uses a protocol named SOCKS, S-O-C-K-S, and there are two different protocol versions, version 4 and version 5, and the Tor network and the software supports both these versions. Version 5 is a little bit more complicated, but version 4 should be very easy to implement. And it will be perfect to do it in C. So that's the task of today, creating our own client for that SOCKS proxy and use it to connect to the Tor network. So how do we start? I'm gonna start by logging into my CodePlanet server like this and prepare my screen as I usually do. Today I'm not gonna be coding in Nano or VI like I usually do. This is a little bigger project, a little bit more ambitious. Could do it in VI, even though it's a big project, but I'm gonna be using VS Code today actually. I'm gonna do my while true command so I don't accidentally close down my screen window like this. And since I am using a remote server, I need to somehow either upload my C files and stuff to that server or code remotely in VS Code somehow. And I'm gonna be using a tool which is called the Sociopath SCP client. Like this. If you want to download Sociopath SCP client. It's a tool that uses the SCP protocol, which is basically installed on every server, to upload and download files and subdirectories. And there's also a remote file editing feature that we're going to use today. Okay, so let's begin there. I have started up the program, which looks like this. So I connect to my CodePlanet server and I go to my code folder. So on the left side is my local hard disk drive, and on the right is the files and directories on the server. So I'm gonna right click and create a new directory, which I'm gonna call Toralize, like this. And now I'm gonna select the Toralize, I'm gonna right click and I'm gonna click open in editor. Then it's gonna download everything in that folder, which is currently empty, but if it were any code files in that folder, it would download it to temporary directory and open it in VS Code. And each time you save or create a file or a directory inside of VS Code, it automatically updates on the server. Okay, so now I have this emptied here. So I right click and create a new file, which I will be calling Toralize.c. And I will also create a Toralize.h, like this. And I will begin by putting a small header. So Toralize.c, and I will include stdio, create a main, and this time I will type out the longer signature for this main function. That is the argument counter and the actual argument pointer, like this, because I'm not going to be using that in the final version, but the client that we're going to code today, that will be it will be used like this. So if we run it by doing ./Toralize, we're gonna enter an IP address like 1234 and a port. So this tool will connect to a predefined proxy server. We're gonna put that in our H file. Let's do it right away. Toralize.h, and let's put the include in here instead. And in this file we're gonna include our local file. So when the file is in your directory, you use quotes around it, like this. And I save this file. Now, if we go into the sociopath window, we can see in the status bar down here at the bottom, Toralize.c has changed, successfully updated to server. And if we go into our terminal and go into the directory and check the contents of this file, we see that it has updated. The .h is not here yet because I haven't saved it. It uploads on save. So let's do that. And with regard to the proxy server, I will be using the default values for the Tor package, and that will be using the IP address of 127.0.0.1. That's the IP address of localhost. And let's call this proxy. And I will also make a constant definition for the proxy port, which is 9050 as a default setting. Save. And just to verify, now we should have both of these files here. Right. So both the C file and the H file. Great. So let's just create the most basic things first. I will create a char pointer for the host name. That is the host name that we want to connect to at the end, so to speak, the server that we want to connect to. And we also need to have the port number. Let's just do an int for that. Yes. Okay, so first I will just check that argc, if that is less than 3, which means that we don't have 2 arguments specified on the command line. Then I want to print to a file descriptor which is called standard error, which is used for error messages. It's like printing to the screen, basically. And then we want to do like this, usage host port, like that. And as an argument, we're gonna give argv0. So argv0, if we on the command line specify /toralize 1234 port 80, then this is argv0, this is argv1, and this is argv2. And this is an error, so we'll return -1. And if we have our arguments, we will point the host towards argv1, and we're gonna set the port to, and we can't just do it like this, because the port is an int and this is a string. So we need to use a function which converts a number in a string format to a regular number, a to I. Let me just check if that requires an include file, and we do that by doing man 3 a to I, and we need stdlib.h, which I will put in our header file. Include stdlib.h, and I will also put in string.h and uni.std.h. These are the 4 that I always put in every C program that I do. Let's line up this a little bit better, like this. Okay, So how will this work? We need to figure out how the proxy protocol SOX version 4, how does it work? So let's go to Google. And if we want to have the technical specification of a network protocol, we do like this. We search for the protocol name, SOX4 in this case, and we add RFC. That stands for request for comment and is the standard way of describing an official protocol. So that way you will always get the right one. And I'll take the first one here and increase the font size a little bit. This is not a huge file. Some of these RFCs are very big, but it is quite a simple protocol. So there's a two-step process. First, you make a TCP connection towards the proxy server, like any other server, like exactly as you did in my web server video and in the TCP client video. Then when we are connected, we need to create a network packet which looks like this. So from left to right there is a 1 byte field that is 8 bits for the VN number, and as we can read here, that's a SOX protocol version number, and it should be 4. Then we have something called CD, and CD is the SOX command. It's the code for the command and should be 1 for connect. So there are two different types of operations that you can do through SOX4. It's a connect operation and a bind operation. So basically a connect operation is when you connect outwards, and a bind is when you prepare for an inbound connection towards you. We are going to do a connect, so we will put a 1 in that field. Then we put the destination port number, and we need to format that port number in network byte order, which is basically that we switch, we cut up the 16 bytes in 2 parts, and we swap them. And same with this destination IP, but this is a 4 byte field, so 32 bits, regular int size, and that's where we put the IP address of the remote server that we want to connect to. And then we need to put a user ID, and I will just put Toralizer there, doesn't matter. And then we need to end that string with 0 byte as usual. And that's basically it. We send that packet, we get a reply, which looks like this, and the only interesting field is this CD field. If that is 90, then the connection has been established, and then you can just send whatever you want. If we get another number than 90, then something went wrong, and we need to deal with that. And then we will send some data just to see that it works. So that is what we need to do. Okay, so I will do like this. I will copy this, and inside our header file I will create a comment block and paste in this one. I want the last line as well, so I see the number of bytes. I think I need to change the size here. Okay, this way we see enough. But in order to be able to create a structure that corresponds to this design, we need to be able to create fields that has the 8-bit size, the 16-bit size, and the 32-bit size. So let's start there. We will use the typedef command to create our own variable types, which will be called int8, int16, and so on. So if we begin with the int8, that's basically an unsigned char in C. That's 8-bit size. So we'll type typedef unsigned char and then our name for it, int8. Then we need the 16-bit size, and that is an unsigned short int. We'll call it int16. And then we need a regular 32-bit int. So that's an unsigned int. And we'll call it int32. Okay, so now we have the different parts that we need. Now we're going to create the actual structure for this packet. So we'll create a struct, which I will call proxy request. And the first is vn, so int8 vn. And the next is cd, which is also an 8-bit. Then we have the destination port, which is 16. Is port. And then we have a 32-bit destination IP field. And then we have the user ID, which has a variable size, but I'm going to create a username of 7 characters, because that way we can have a 64-bit variable here, which ends in a 0 byte. So that's why 7 and not 8. So basically I will do unsigned char user ID 8. And this is all we need for the first structure. Let's create the other one at the same time. This one is a little bit smaller, so struct proxy response, and we're not going to be using all these fields. So if we look at this one, the VN is always 0. And the CD will have the code. So the CD is the only interesting field here, because the remaining fields are ignored. So destination port and destination IP are ignored, but we still need to have them defined because we need to have the right size of this packet. So I will do it like this. I will start by creating an 8-bit integer for the VM and an 8-bit CD. Then I will just do int 16 and an underscore character, and then int 32 and 2 underscore characters. We could name these according to this, but I think this clearly shows that they are not important. Okay, so now we have our two structures. We can remove those comments. And make this a little bit bigger again. And I want to create a type def for these structures, so we don't have to type the whole proxy request every time. And I will just call this rec with a big R. And same here, type def struct proxy response, and this will be res with a big R. Okay, so now we have prepared everything we need basically in this file. And we do need a couple of includes though, because we are going to use the following functions. We will have a socket to initialize the socket. We're going to have connect, and we also need close, h-ton-s, and inet address. So remember what I told you about the network byte order. So if we have a port number, for example, like something like this in binary, so this is a 32-bit, no, sorry, 48. This is a byte. So if we do like this, let's say this is a port number, and I don't know exactly what it corresponds to, but let's say for instance that it's 9050, because it's a 16-bit field, so it looks something like this. Then we need to copy this right part and put it to the left. That is network byte order, that we have the most important bits first. And that is what these two functions are for. h-ton-s does it for the port number, and the inet address takes a string and creates a big. So basically it first takes this IP address and translates it to a big number, and then it makes this network byte order. So these are the functions we need. Perhaps I have forgotten any other ones, but that will be clear when we get to that point. So let's find out what include files we need. Let's begin by socket. We do man to socket and y2 because this is a system call. That's what. How do you know if it's a system call or a library call? Try a library call first, a 3. If you don't get a hit, or if you get a hit that doesn't seem right, try the 2. Okay, so we need syssocket.h. I'll just copy it right on. This, and then we need the connect. That's also a system call. So man to connect, and that's the same. We don't need it again. And what else did we need? Close. I think that's UniSTD that we already have, but let's see. So the close, that is also a system call, and we use it to close down the connection. Can also be used to close down a file. Yeah, UniSTD, we had that already. And then we need the hton_s and inet address. So man, this is a 3, so hton_s. This one. And finally, inet address. Also a library call. So 3. Here we need a couple of include. Syssocket we do have already. ARPA inet we do also have, but not net inet. Okay, so let's see if this compiles. Since we are using a couple of files, I think I'm gonna create a make file as well. So I will create a new file and I will name it make file with a big M. And then I will just put in all gcc toralize.c-o toralize. We're gonna be adding a lot of stuff here later on, but for now this ought to do it. So let's save, and when we have a make file like this, then we don't need to issue the gcc command every time. We can just do make, and then it will try to compile. Okay, typo. So let's go into the toralize.c, and this should be an if, not an int. Let's save, and we'll run make again. This time it compiled our tool. Okay, so the next step is connecting to the proxy server, because we're not gonna create a TCP connection directly to this host and port that we specify on the command line, we are going to connect towards the proxy IP address from the H file and the proxy port 9050. So that we have done before, creating a TCP client. It's exactly the same as before, so I'm going to make it quite fast. If you need to learn how to do that, you can watch either my TCP client episode or my creating your own web server series. I will explain by haste though. Okay, so we need a couple of variables. First of all, we need an int, which is called s, for the socket file descriptor, return value. We also need a structure, which is called sock address in, and I'll call this sock. That's where we specify all the IP addresses and stuff. Okay, so let's start by creating our socket. So s equals socket, and this is pretty standardized. We always put in sock inet, and second argument is sock stream for a TCP connection, and then a 0 for the third argument. And if this s is less than 0, then I will use the p-error command to easily print an error, and we will specify which function that produced that error. And then I will just return -1. When we create the final version of this, I'm going to use more accurate error codes, but for now we'll just do -1 for everything. Then we will create, we will prepare our structure, and that's 3 things we need to add in order to make a TCP connection. First of all, we need to put the SYN family to AF inet. We need to put in the SYN port and use the hton s, so we get it in network byte order. And then we will just put in our port variable here. And finally we will put in our sock SYN address s address, and that will be equal to inet address and our, no, not our port, it should be our proxy port, and it should be our proxy IP address, nothing else. Okay, so these are the 3 things. Now we need to initialize the actual connection with the connect command. So we do connect, and we reference the socket. The second argument is our structure, and we need to create an explicit typecasting, because we need to change it to sock address struct, a pointer to a sock address struct, and we also need to send the reference. So let's put an ampersand there and the sock, and then we need a size, and I will just do size of sock. That ought to do it. Okay, so this line will connect to the server, but I will also need to do an if statement so we see if it succeeded. And this should return a 0 if it works. If we wouldn't remember that, we can go into the command line and do man to connect and go towards the bottom, and here we will find a section for the return values. If the connection or binding succeeds, 0 is returned. Otherwise, -1. So I will just do a simple if statement. There's no need to save this to a variable. So if this is not 0, something went wrong. And then we do p error. Connect. And return -1. Otherwise, we are connected to the proxy server. So I will just echo that to the screen so we know what's happening. Then I will close the connection because I want to see if it works. So close S. Return 0. Okay, let's see if we did something wrong. Make it compile on the first run. That's not every time. And let's run it and see what happens. Right, we need to put something here. We're not going to be using that information at the moment. Connected to proxy. Great, so it works. So now we have successfully created our TCP connection towards the proxy server, and the next step is to create the proxy request packet according to this structure that we created before. We haven't created any function declarations, so let's do that as well. So we have a main function, takes in an int and an argv pointer, and when I create those signatures, shard, of course. So if we look at our regular main function, we use this format right here. So a char array of pointers. But when I create the type signature, I usually use this format. Doesn't really matter. Okay, so that's the only function that we have this far. Our other function is going to return a pointer to a request. And let's name this function request. And as arguments, we're going to take in a char pointer, which is our destination IP, and just a regular int for the destination port. And let's make both of these const as well. The const keyword means that we cannot change these variables inside of the function. So it's just input values. So this is the signature. I'll copy this and then I will strip it down so it looks like our main one, because we don't need to have the names of the variables when we do a function declaration. And why do we do these function declarations? Do we have to? No, we don't have to. But imagine that we put our main function in our C file at the top. If we then try to reference the request function, it's not going to find it because it hasn't been defined yet. But if we put our request function on top of the function declarations, then it will work. So that's one reason. But I think a more important reason is so you can have like a better look. You can just watch the .h file and you see the entire structure in a very good way. So always do this if you have multiple files or a big .c file. Okay, that was a small parenthesis. Sorry, I copied over this one. There we go. And then we go into here and we will create this request. So what do we need in order to do that? Well, we need to allocate the memory for this request structure that we're gonna return, and we are gonna reference the length of the structure a lot of times. So I'm gonna create an alias for that, or a macro, and you do that using the define, and then you give it a name. I will call this rec size. And what is rec size? It is the size of struct proxy request. And let's create one for the other one as well then. Define a res size, response size, and that is size of struct proxy response. In that way we don't have to manually type out this as soon as we need to reference the size of the structure. And now semicolon at the end. Oh, I misspelled. There we go. Okay, so back to the .c file again. And I'm gonna create a request pointer. I'll just call it rec. Sorry. And I'm gonna start by allocating the memory for this structure. So request equals malloc rec size, like this. And now we're gonna fill this structure with the correct data. So let's bring up the RFC again. So the first thing is the VN, and the VN should be 4. So rec VN equals 4. And if you're not familiar with this arrow, that's basically the same as the dot format. But when you're using a pointer to a structure, you use this arrow to indicate that we need to grab into the reference in order to get the value, or set the value in this case. Okay, so VN is 4. Then we have the CD, and it should be 1 because we're making a connect request. So rec CD equals 1. Then we have the destination port, and we need to put it in the correct format. So rec dest port equals, and now we use this h-tone-s function that I talked about before to switch it to network byte order, and it is the destination port. Then we take the destination IP, so rec destination IP equals inet address destination IP. And then we need to have a null terminated string with our variable, and I want it to be 8 characters. So let's create a definition for that. Find username Toralizer, because we need to remove this E. So 1, 2, 3, 4, 5, 6, 7, and then a 0 byte at the end. So I will use string copy to copy into the rec username the username, and the maximum size is 7, and then it will add the 0 byte. Let's do 8. Okay, so now we have prepared this structure. And now we will simply return it like so. And now it will be very easy to handle this, because we have a function which just creates the entire data that we want to send, and we know the size of this structure, so we can just use the right system call in order to send it. Okay, so now that we have our function which creates the packet that initializes the proxy connection, now we're going to use it. So let's go into our main function and let's create a pointer of our structure request type, so we can use it when we want to send the data. And instead of just closing the connection like we have done here, we're gonna set our request variable and use our function. And our request function takes two arguments. It is the destination IP and destination port. And we do already have variables for that. It's the host and port variables. So we'll just use them. So host and port, like this. So now the rec variable is pointing to our packet, and we just need to send it using the right system call. The first argument is our socket file descriptor, which we named S. The second argument is the buffer, and I think we only need to do rec. Perhaps we need to do, yeah, we probably need to do a type definition, typecast I mean, but let's put it like this to begin with, and watch the warnings and errors when we compile it. That's usually the best workflow. And we need the size of the packet. And since we know that we always want to use a 8-byte an 8-byte buffer for the username, we have a constant size of our request packet. So we will just use that definition that we put in here somewhere. It is, I think we created a macro, yes, rec size, that's the one. That is the size in bytes for how big this packet is. So now we send that packet, and the next step in the process, if we look at our RFC, it is accepting this structure back. So we can look inside of the CD property and look for the 90 code. So how do we receive this one? Well, we did use write in order to send the data, and we will use read to receive the data. And for that we need a buffer. So I think the easiest way will be to just create a variable on the stack for that. So buff, and then we'll put the response size as the number of bytes. And before I use read, I always want to make sure that the buffer is empty. So I will memset the buffer with zeros and use the res size, number of zeros. So now we have a clean buffer that we can read data into. Yes, so let's do read, and the first argument is the socket file descriptor, second argument is the buffer, and the third is the size, like this. And if this read operation returns something less than 1, because the number of bytes should be returned, then we know the operation has failed, and we need to show an error. Sorry, I'm a little bit used to the JavaScript strings. There we go. And let's free the buffer. No, not the buffer. Free the request packet, so we don't have things lying around on the heap. And let's close down the socket file descriptor and return -1 for now. So this is if the read operation fails. If it has succeeded, we should have a packet that looks like this in our buffer, but we can't easily access the values inside of it if we only have a string pointer. So we need to create another pointer of the correct type, which is our structure for the proxy response. So we will create a res as well as the rec. And we should just be able to point this towards the buffer. And that's what we'll do. So res equals buffer. I think this should be enough. And now we should be able to grab this value, the CD value, and I like doing it like this. I will create an int, which I will call success, and this will be a Boolean variable. But as you know, we use ints as booleans. We can use char and other types as well, but usually it's int. And this will be used as a predicate. I'm not sure if you are familiar with the term, but a predicate is basically a function or an operation that returns true or false. And this is American English. I think in the British world they use the word property for this. But since we already use the property term when we describe other things, I think the predicate is a better term. Anyhow, then we can do something like this. So we set success equal, and we go into the structure and we check for this CD value. And I will put this in parentheses, and we do like this. So what does this mean? This means that if the CD is equal to 90, then success will be equal to true. If it's not 90, success will be false. Which means we can do like this to see if it has worked or not. And then I want to print out an error message of my own. So I use the fprintf to the standard error way. And I want to say something like unable to traverse the proxy error code, and then the error code. I need to divide this a little bit. I'm not sure you know it, but if you have a large string, you can always divide it by smaller strings and put them on different lines. Make sure to encapsulate them in quotes on both instances. And then we will show the res2cd value like this. And we can also do, let's close the S and let's free the rec and return -1. And unless this if clause happens, we have successfully traversed the proxy. So let's inform that with a printf, at least for now. Perhaps we will remove these messages when we are done. Okay, so successfully connected through the proxy to and we will have a %s:%d, and then I will use host and port like this. And now I will close down the connection. When we finish this program off, we will not be closing down the connection. But since we are only checking right now if it works, if we are able to connect through the proxy, we can close down everything and terminate when we are done. So this code will be removed in the final version. And we will free the rec and return 0 like this. The indentation seems to be a little bit off. Well, we'll see if we get an error. Okay, so let's compile this and see what happens. Okay. And when we are troubleshooting code, especially when we have coded quite a lot of lines of code since we last compiled, always look at the first error, because sometimes if you fix the first error, all the other errors goes away. So don't get discouraged when you see a full screen of error messages like this. Just focus on the one at the top. So what does it say? Rec has no member named username. Interesting. So let's go into our H file and see what we've got. User ID. Okay. Yes, of course. So where was that? That's probably inside our request function, right? Yes, here it is. So user ID. Like this, okay. And before I run make again, I press enter a couple of times. So we get a barrier. That way it is much easier to see where the last couple of error messages stops and the new batch starts. Okay, so assignment to res star from incompatible pointer type. Res equals buff. Okay, that's the one I was a little bit unsure about, remember? And I said, let's compile this and see what it says. Because in some of these cases, the C compiler will perform an implicit typecast in this case and work it out anyway. But not this time. So okay, so res is a struct pointer and buff is a string pointer. So what if we were to just do res like this? Let's try that first. Seems like it worked. Okay. So close S, data definition has no type or storage class. That's an interesting error message. Data definition has no type or storage class. Close S. Int close, int fd, uni std. Do we have all our include files? I have never seen that error message before. Uni std, yes. Didn't I call that variable s? Yes, and that's an int. Int. It was only a warning, but a very weird warning. Perhaps something else is wrong in its proximity. If success, Printf and the parentheses, then we have the string and then the end parentheses, close S. What line did it complain about? 94. Okay, it's not this one. It's complaining about this one. Well, there is. Okay. So, let's see. If success, and then we have this, close S, close rec. Yeah, this shouldn't be here. Okay. Let's do this again. Okay, it's compiled. Let's see if it works. So what shall we connect to? I will just do one of my web browsers, and you might have noticed that we didn't put any DNS related stuff in this one. So I can't just put in www.networktechnology.org or something like that. That's something that you probably can add by yourself. See that as an extra task. But for a proof of concept, it's not really necessary. Okay, so I will take the IP address of my web server and let's run Toralize against that on port 80. And if this works, we should see a message that we have successfully connected to the proxy, and we should also see a message that we have successfully connected to the end host through the proxy. Connected to proxy, successfully connected through the proxy to blah 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 blah. Okay, very nice. So this has accessed the web server through the Tor network. And let's add some functionality so it can send some data and read some data, so we can see that it can communicate with the end host as well. That is also stuff that will be removed in the end result. So let's create another buffer. Let's call this temp, and let's do 512. Since it's only temporary, I will not think much of it. So here we are successfully connected, and now I want to send something. So since I'm connecting to a web server, I can use the head command just to grab the information about the web server versions and stuff like that. That's quite easy to do. So I'm going to use the smprintf in order to create the buffer. But first I want to use the memset in order to zero the entire buffer. So, no, not buffer. I need to remember I call it temp. And 0, and the number is 512. And then I will do smprintf, and we are gonna put the result into the string variable, the buffer, that we call temp. And we won't be writing more than 511 characters. And what do we want to put there? So let's do head HTTP like this, and we'll end by RN. And on the next line, I will put in host network technology.org. And if you wonder what this RN is, sorry, that is the Windows standard for new lines. So this R thing is a carriage return, which jumps down and goes to the left, or it goes all the way to the left, and the N is, as usual, the line feed. Okay, so now the buffer contains this data. And then we will just simply send it. So write s temp, and I'll do the string length of temp like this. And then I want to zero out the buffer again, or not the buffer, the temp. And then we want to read the results. So we read from S into temp and no more than 511 bytes. And then we'll just print that to the screen with a regular printf like this. Let's put it in single quotes as well, so we see if there's something weird going on. That's a good tip, by the way. Like if there's a line feed before the data or something like that, then we will see it like this. So this will be on one line and this will be on the next line. Okay, save, and now we will compile, and let's run it again. And this is the response from the web server. As you can see, it works. We are able to communicate through the Tor network, and if I connect to my web server, we should be able to check the logs and see what IP address the requests came from. Var log Apache. Here we are. And let's do tail-3 access.log. Okay, so here is our head, and if we grab this IP address, we see that it's some kind of German address. And we can also do, if we restart the Tor server, so we do etc init Tor restart as root, restart like this, then we issue the same command again. We did get the output like before, and if I check the logs once again, we get another IP address this time. And if we do a host on that IP address, we see that this time it's in the Netherlands. So our program works fine this far, but at the moment it's just a proxy server client. It's not doing what we intended it to do from the beginning. You remember, I want to be able to do something like Toralize and then run any command like curl against some IP address, and then I want to intercept the connection. I want to run this command as is, but I want to intercept the connection that the actual program does and run my code instead. So it tunnels through the Tor network any program that we want to run. So we can do Toralize and put anything here. We could do like, if we have Firefox installed in the same directory, we could start Firefox with Toralize, and then it will be tunneling through the Tor network. And we could do telnet or SSH. That is what I want to do. And that is the next step in this process. It seems really advanced, but you will see that it's quite a bit easier than one might think. So what have we learned today? Today you have learned how to create a SOX version 4 client and use it in order to connect to the Tor network. And next time you're gonna learn how to create this nifty little tool that I call Toralize. If you like this episode and want to see the continuation or other stuff in this channel, please subscribe to this channel and hit the like button if you think I deserve it. And thanks for watching, and thanks for today. Okay guys, welcome back. Last week we began creating this Toralize tool, which tunnels any Linux application through the Tor network. We wrote the first part of it, which is a SOX version 4 client. So this is what we have this far. We can supply the destination host and port. So let's take my web server as an example. So we run Toralize, and let's do this IP with a port of 80. And we connect to the proxy. Maybe it's okay, there we go. Sometimes when you use the Tor network, it's quite slow, but more often than not it's quite fast. But as you can see, we connected to the proxy. We successfully connected through the proxy to the destination, and we communicated with the web server on the other end. So the biggest part is done. What we need to do now is the following. We need to turn the client to a library. So instead of using it as an application, we want to have it as a library, and that is a shared library, to be specific, .so files. When we have done that, we're gonna turn main into our own connect, replace regular connect, and we're also gonna save a reference to the original connect so that we can use it ourselves, because our current tool is using connect. If we look right here, so we connect to the proxy server using that system call, and that's why we need to save a reference to it so we can use it ourselves. We also need to grab the IP and port from original connect. So we will take care of the arguments that the application sends to its connect, and we need to take the IP and port from there instead of reading it from the command line arguments like we do now, and then we can proceed by doing what we do now, and then we will just leave it to the original application to take care of the rest of the communication. So we do our thing, and then we exit our function and let the program take over. Okay, so how does this technique work? Well, when you compile your code, you have two options. You can compile it statically, so it's statically linked, and that means that if you use any library calls, or system calls too for that matter, like Printf or anything, that will be, that code, the Printf code, will be saved in your program's executable file. But that's not very optimized, because if every tool on the whole drive would be statically linked, then there will be a lot of duplications, because almost every application uses some form of library calls or system calls. So that's why we have the shared libraries. So instead of, and that's what's usually in use. So we have like a database with a lot of, with a printf code and with a scanf code, and even wrappers for system calls like connect. And when an end application needs to use any of that code, it will collect it from the central repository on the disk. So that's how it works. The thing is, there is a kind of prioritization order, so which we can influence. So if there are two functions with the same name, which one that's gonna execute is decided by a list, basically, and a prioritization order. So if we name our own function connect, and we have compiled this as a shared library, then we can make any application use our code as priority 1. And in that way we can intercept and hijack the library call and system call, because all system calls have wrappers in the libraries. Okay, this will probably be a little more clear when we have written the actual code, tested it. And this is not my own invention, this technique. I am following a website. Let me just find it. C shared library function hook. Here it is at R. Jordanes. So it's pretty simple actually. So put s is a function which basically works like printf, but not as advanced. It prints a single string on the screen. So that's the one that he uses in his example. So as you can see, he creates a function with the same name and same signature. He creates a function pointer also with the same signature, and that is for saving the original put s in this case. And then he gets the reference from this DLSym function. So basically you give the RTLD next and the name of the function, and it gives back the memory address where that function is originally located in memory. And then he just does like this. So he checks if you send the argument hello world, and in that case he hijacks the original put s call and changes the message. In other case he just runs the original put s with the same arguments. So this is basically what we're going to do. We're not going to have a condition because we are always going to hijack the original one. We are, however, going to use the original connect function to make our connection to the proxy server. And then we compile it as a shared library. So there's a couple of additional switches we use. And then we get a .so file. And then we basically tell the system to use our library instead by this ld preload environment variable. So we're going to create a small bash script in our case, 3 lines big, and that's what we're going to name Toralize. And then we're gonna use that to set the environment variable and run the command. And yeah, that should basically be it. So let's begin. Let's start by grabbing the signature. So we do man to connect and just copy this exactly as it is, and then we go up to our main and we just paste it right here. Like so. and sockfd address len t, and we remove this, and so we basically turn our main function into this connect function. Like so, and we create a function pointer. And if you have watched my episode about function pointers, you know that that is done like this. I will paste the signature for this original function once again, and instead of connect I will just name this P for pointer. I'll put it inside parentheses and add the star, and then we remove this part, so it should be basically like a signature function declaration. And we use this to point to this dl_sims function. And let me just see where it's located. So man3 dl_sims, and if we don't find it in page 3, we do page 2. dl_sim, perhaps it's without the s, yeah. Okay, so it's inside of this dlfcn.h. So let's add that to our list of includes, and let's see if he included anything else, only the string. So, and I need to grab the first argument, rtld_next. And you might ask why I don't copy paste, and I try to avoid that when possible, because if I type this a couple of times I will probably remember it. rtld_next, and the name of the function is connect, like this. And we initialize the socket, but we don't really, or let's do it like this, by the way. The curl application, or whichever we use, have already initialized their socket, but I think it will be easier just to pipe those two sockets together. Okay, so let me update the signature here as well, so I don't forget that, by the way. Because we don't have any main anymore. We just have int connect. It's int, right? Yes. Did I do int here? Yes. Okay, so int connect, int const struct sock address star sock len t. So we don't have a main anymore, because that's only for applications, and this is not an application. This is just a couple of functions which are free. Okay, so the application runs connect, and we don't need any of this, and we save this, we initialize our socket, and here we make the connection to the proxy server. Nothing will change about that, but we're not gonna call connect because we would be calling ourselves. We will be calling this P, the function pointer, like so, connected to proxy. And we also need to change our request function. Instead of sending host and port like we did before, let me remove that. So we have int s and we don't have this host. Instead, we need to grab the IP and the port from the arguments. So this is what the application provides. We have the socket file descriptor, we have the length of this structure, and we have the actual structure. So I think the easiest way would be to, I don't want to name this address. Let's call it soc2 and s2 instead. So S and soc, that's ours, and S2 and soc2 are the provided by the application. So we need to look inside of this and get the data that we need. So let's pass the whole structure of that instead as host and port. So we'll just do soc2 right here, and we need to change the signature for our request function, and that is of type struct soc address in and star, struct soc address in star. And I think we need to do a typecast and send the reference. So where were we? Right here. So struct soc address, struct soc address in soc2. I think we need to do it like this. If we get a warning or error, we will change it, but it should be alright. Struct soc address in soc2. So we send that whole structure to this function, and we need to change this as well. So that will be struct soc address in, let's call it soc. No, let's call it soc2, so we know what's what. Okay, so the destination port, we don't need to do HTON-S and INET address because it's already in the network byte order. So the only thing we need to do is reference soc2 syn port, and for the destination IP, soc2 syn syn address source address, like so. Perhaps we need to do some typecasting, but I don't think so in this case. Okay, so now we have the correct packet, and then we save that, then we send that packet. Unable to traverse the proxy. We can keep this for now. Successfully connected through, and this we will not have though. So as soon as we are connected, we are basically done. We don't want to close the socket. We do, however, want to pipe our socket with the end applications socket. So what does it mean, piping? Well, we need to do so everything that's being sent to S will also be sent to S2, and everything that's being sent to S2 is being sent to S, and same with the receives. So we basically become the man in the middle. And there is a good system call which is called dupe2, which does exactly that. So it creates a new file descriptor, and it will be the same value as the second argument, which means that this will be pretty seamless if we give S2. So dupe to S2, and then we return. Did we forget anything? I think we did most of it. Let's copy the compilation flags from this one. So we'll go into our make file, and this will be toralizer.so fpic shared lel. Okay, and I will begin by removing the Toralize binary executable because that won't be necessary. Okay, let's see what it says if we try to compile this one. Okay, dlsims, it should be dlsim. Right here. And I enter down a little bit and run make again, and host undeclared. Okay, that's the message. I don't think we actually need that one. Where is it? Unable to traverse the proxy. Successfully connected through the proxy. Let's just say through the proxy. Enter. Otherwise we need to convert between network byte order and stuff like that. Perhaps we can change this later on instead, if we want to. Okay, it compiled. So how are we going to test this? We haven't really created our bash script. We can do that now, by the way. Let's begin by checking what directory we're in and the name of this. So I'll just do a copy paste of this directory, and I will add this SO file to it. So this is the whole path to our library. And I will log in as the root user. I will go to user bin, and I will open up Toralizer. And this will be a bash file. So we need to have this interpreter at the top, or the hashbang. Okay, so let's export LD preload to this one, and then we want to run the commands, because we're going to run this as Toralizer and then curl or whatever. So we need to send everything that's on the right of this Toralizer. And there is a way to access all the arguments at the same time, and I think it is done like this. Okay, so first we export the LD preload and point it towards our shared library. Then we do the $, and I think it's the @ which will run all the arguments to this script. And finally we unset the LD preload like this. It's probably not necessary to unset it because it's the end of the script, but I think it looks a little better. Alright, so we save this and give it running permissions. Toralizer, and then we test it out and hope that it works. So network technology.org. We will try to do Toralizer, curl, and an HTTP request against this IP address. Connected to proxy. Couldn't connect to server. Let's try restarting the Tor. Perhaps it's a bad connection. That happens sometimes. So Tor restart. Okay. And then we try it again. Okay. Connected to proxy. This time it didn't even give an error message. Let's see what this error code 91 is. If we go back to the RFC, so RFC SOX4. And we go down here. Request rejected or failed. I will try once again to restart the service. Perhaps we are unlucky with the connection. So let's do like this. And then we run Toralizer again. At least it's able to intercept the connect function, as we can see by this connected to proxy. But it doesn't really succeed in connecting. Let's just see that this one is up and running. Yes. And it's listening on port 80, right? Let's do just like this. Okay, I don't have telnet here. Let's run it from this instead. So end of telnet this port 80. Okay, it's the server that's not responding. That's weird. Host. Let's try something else. Let's do, I think we should be able to do a regular host name. This is a Swedish site that shows the IP. If we do make this work though, that's not going through the Tor network, the actual DNS request. So the DNS request probably goes outside of the Tor network, and then the actual IP connection goes through. So couldn't connect to server. Weird. Does anything work? Google SC. Yeah, there's nothing wrong with the routing. But we need to try something else. What if we do a host on this site? And we Toralize a curl HTTP and this IP instead. Are we able to connect directly to this one? Okay, that works. Let's look through the code. Perhaps we did miss something. So what happens right here? We set this to the regular connect function. We initialize a new socket and we connect to the proxy with a proxy port using this the regular connect function, and we manage to get connected to the proxy. Everything is fine this far. Perhaps there's some problem with when we grab the IP address. So rec equals request struct sock address in. Perhaps we should not send the reference. What if we were to do like this instead? cd code and Toralize, and we need to run make then we do host ip.sc, and we do Toralize curl http and this IP. Okay, so now it works, and we should be able to see the IP here, I think, somewhere. Okay, it seems that we go through some kind of middle server. It probably only works against Swedish IP addresses, and we probably don't come from a Swedish IP through the Tor network. We need to try something else. What if we were to do... First, we can test regular first. So if we do host... what is my IP.com, we do a regular curl, and we get an error code. Okay, we need to send the host name, and I don't think that'll work, but let's try it again. So curl, or it will work when you do it right here, but I don't think we will get a response. No. Let's just do Google then. So host google.com, and we do Toralize curl http and this IP. Okay, that works. What if we do a host name? Does it even try to resolve that? Yeah, it works. But as I said, be careful by doing that, because only the IP connection will be private, not the DNS request. But as you can see, we are able to traverse the proxy, and we are able to Toralize any command using this tool. So that's the end of this series. I hope you want to subscribe and like if you think it deserves it. And there will be more interesting videos in the future. Thanks for watching, and thanks for today. What's up, guys? In this episode, we are gonna code our own encryption library. It is loosely based on the ARC4 cipher, but with some improvements which makes it more secure. We're gonna expose a couple of functions from our library, and it's an initialization function which takes a key as an argument. There's a encrypt function, and there's a decrypt function, and finally an uninitialization function. So it's very easy to use, and let's get started. Hello everyone, and welcome to today's show. Today we're going to code our very own encryption library using the ARC4 algorithm. When talking about encryption, that is one of the more easy encryption ciphers to implement. But it's a little bit bigger project than we usually do, so I will not be coding inside of the terminal today. I will do most of the work through VS Code. So let's begin by launching the Sociopath SCP client, so we will be able to code live against the server. I will just go into I will put it in my temporary directory, and I will create a new directory, and I will call this arc4, spelled like this. So the algorithm is written like this, RC4, but it's pronounced arc4, so I think that's a good name for the library. So I will simply create an empty folder, and I'll right click and open an editor. Then I will have access to the entire folder inside of VS Code, like so. And I will minimize my Sociopath and close down this. And I will also log into my server and attach to my screen, or I will create a new screen instead. And I will configure it, and as you run command vbel off, and as usual I will write a simple bash script like this, just so I don't accidentally close down this window and terminate the screen. So let's go into my temp directory and go into my arc4, and here we are, an empty folder. So what do we need? I will create two files, or three actually. First I will have the actual code, the arc4.c, like so. And as I save, we can see here it's successfully updated to the server. And we will also need a arc4.h for our structures and includes and definitions and macros and such. And to make our life a little bit easier, I will also create a make file, which is going to compile the whole thing. And actually, I will create a fourth file as well. This is just a temporary file. We won't need this file when the project is completed. But as we are implementing this encryption, it will be easier if we have an example program which we can use to try things out. And I will call this example.c, because we are creating a shared library. So this library will be used by different C projects, and that means that the arc4.c file will not have a main function. So this example.c will provide our temporary main function so we can run it. Alright, so in the make file I will simply define the stuff that needs to be compiled. So the first thing will be arc4.o, and you write it like this. So the file that's the target, and then a colon, and then you write the dependencies. So this file will depend on arc4.c, like so. And then you tab and you write the command. So I will do gcc-c arc4.c, like this. And I will also turn on optimizations at the highest level, as well as log messages. And when that file has compiled successfully, we will have an arc4.o, and then we will create the actual arc4 library. So this depends on arc4.o, and I can't really remember how to let's see, all the flags necessary to create the shared library. So I will check how I did it in my Toralizer makefile. And I will simply copy this part right here. So I will do gcc, and we are compiling arc4.o, or linking actually, and the output will be called arc4.so. That's the extension for a shared library, and we want the optimizations and the logging, and then this additional flags necessary for a shared library. Okay. There we go. So after those two steps, our library is compiled, but I will also have the example .o dependent on example.c, gcc-c example.c, and I will turn on optimizations and wall. And when we have the object file, we can compile example, which will need example.o, and then we simply do gcc example.o -o example wall 02. And I would also create a clean, which simply removes everything besides the source files. So all O files, all SO files, as well as the example binary executable. And then I will just tell the makefile what we should do as a default when we run the command. And I want to compile arc4 and example. So this is our makefile. If I didn't miss anything, I think we should be able to let's just go into the temp and the arc4, and I will set this to my home so the prompt won't be so big, like this. And I didn't save the .h file, I think, and the example and the make file. There we go, arc4, make file, arc4.h, and example. So I should be able to run the make now, and we get a reference error for the main, but the .o file should have been created. Yes, they did. So everything seems to be working. Even the SO file did be created, even though everything is just empty source files. And if we do make clean, we're back to where we started. Okay, that's a little bit of administrative work, but it will pay off when we need to recompile and debug our code. I'll close down the make file because we don't need to do much with that. And I will actually start with the example file because if we create the example first, then we have a kind of a roadmap to the different functions that we need to create later on. So I think that's a rather good way to start. I'm gonna include the arc4.h, arc4.h, and inside that I will have my regular definitions. So I usually start by putting in the stdio. That will be removed later on because we're not going to use any of these libraries, but during development I think it's easier to have all the usual standard libraries ready to go. Like so. Okay, so how will this example file work? I'm gonna start by just creating function definitions. So we do everything in the order that you should, even though this is a small file. So we'll have an int main with no arguments, and that'll be all for now. So I'll create the actual main, and I never seem to learn where to find my curly braces on my Mac. Alright, here they are. So I will make this file a little sloppy and easy to work with, because this will not be a part of our production code, so to speak. So I will just do it as easy as it can be for myself. So I'm going to create a couple of pointers. I will have one for the key, and I'll have one for the source text that we want to encrypt. I will have one for the destination text, and I will have one additional pointer for when we decrypt the encrypted text. So let's call this encrypted instead, and this decrypted. That's a little bit more obvious. And I think I need to make this a little bit smaller. I hope that won't be a problem for you. Okay, and I will just define this statically. So I will set the key to, let's see, something easy like tomatoes. When you run this code for real, you should always create a real encryption key. So this can really be anywhere from 8 bits to 2048 bits according to the standard. But this will do as an example. And the text I want to encrypt is a part of a Shakespeare poem. Shall I compare thee to a summer's day? Okay. We will also need to, before we do that, I need to define a couple of type definitions, because I'll be using 8 bits integers, and I will use 32 bits and possibly 16. So I'm going to define those first. So let's define we will do unsigned char, that is an 8-bit value, and I will call this int 8. Not defined, by the way. This should be a type definition. So a type definition is when you create your own type. Everything you write is what the source name is, and the last one is the destination. Okay, so the next type definition will be a 16-bit int, and that is defined in C as an unsigned short int. And I will call it int60. And finally, we need an 8-bit variable as well, and I will type this as an unsigned char int 8. Oh, sorry, I have done that already. The only thing we have left is a regular 32-bit integer, and that will be a regular unsigned int like this. Okay, so now we have our type definitions, and let's continue with the example main function. So we have the string that we want to encrypt, we have the key, we will also have a pointer to a structure, which I will call arg4, and I will call this pointer arg4 like this. So this will contain the internal state of the encryption engine, so to speak. And I will define this as a, let's do it here. I will do struct s. I usually prefix my structures with an s. That's a stylistic choice though. So s arc4, and what will this contain? Well, we will actually use the Wikipedia page. It's a very good Wikipedia page which tells exactly how to implement this encryption. Not in a specific language like C, but with pseudocode. Okay, so we have this, and now that we have the key, by the way, we also need two size variables. So let's do int 16, and what do we need? We need two size variables. So let's call those size key and size text. And I will just use this string length to define those. So s key equals strlen key, and s text equals strlen from. Okay, so now I have all that I need in order to call the first arc4 function, and that is called, let me do the function declaration. It will be called arc4 init, because it initializes the arc4 structure. So this will be of type arc4 pointer, and it will take two arguments. It will take a key. Let's do it like this: unsigned char. No. Let's use our int 8. It's not really an integer because this is a string, but every character is an integer, so it will be okay, I think. So int 8 key int 8, because if I don't do it like this, if I do sometimes char and sometimes int 8, and then I will probably get this signedness wrong, and I don't want that. And we will have an int 16 for the size of the key. And I don't need those. Int 8 pointer, int 16, right? Then we go back here and we will set our arc4 equal to arc4 init, and we send our key and our s key. Like so. And this is a function that might fail but that's very unusual, so I won't care for that during this example program. But if you write a real production grade program, check if this arc4 returns 0, because in that case the malloc returned error. Otherwise we will get one of these structures back and then we are ready to encrypt. Let's add some prints as well. So initializing encryption. And I want to have a way of putting this to the screen instantly. So I will create a definition which I will call f. And I'm not putting this into the arc4.h because this is not something I need in the actual end result in code. This is just for convenience. So f will be f flush std out, and that basically flushes the standard output buffer, so that if I do a printf like this, which is not ending in a new line, it will, and if this takes a couple of seconds to initialize, then this text will not be printed before this delay, which kind of defeats the purpose. So I will put the f right after, like this, and then down new line. Okay. And then let's print out the inputs first. So I will put it in single quotes. And let's do it like this, a new line and then an arrow. And this is the from text, like so. Then we do the actual encryption. So we will use our encrypted variable. So encrypted equals arc4. Let's define this first. So this will return a string pointer, but I will call it an int8 pointer, and it will be called arc4 encrypt. And it will take two arguments, one which will be an int8 pointer, so the string that we want to encrypt, and a size in the form of a 16-bit integer, like so. Pretty similar to the initialize function. And the arc4 encryption works like this. You don't need a specific decryption function, because if you try to encrypt the encrypted text, it will be decrypted. So then it goes backwards. So with that in mind, we can just create a macro which will be called arg for decrypt with two arguments, x and y. And this will just call arg for encrypt with x and y. So it's not really necessary, but it makes it a little easier to use. And in order to make this encryption function work, we need another function called arg for byte, which produces one single character of encrypted text. So this will be an int 8 and not a pointer, just a value. Now that we have our data types and our function declarations done, we can continue with the example.c file. So the encrypted variable will be equal to arg for encrypt, and we will send in the from text, and we will also send in the size of the text, like so. And this is a function which shouldn't be able to fail, which means that the encrypted variable will now contain the ciphertext. The next thing we need to do is create a function which will make it possible to output the encrypted text in some format, because the encrypted text will not be printable characters. It will be any number of different integer values. And I'm thinking about using an output like this. So 1 byte will be represented by 2 hexadecimal characters, like this. So this is 1 byte, and then 2 bytes per group, and each group will be separated by a space. Okay, so this function will not be a part of the library itself, only this example file. So it shouldn't return anything, and let's call it print bin, because it's binary data. And it will take in an int 8 array pointer. Let's call this text. It's not really text, but whatever. And then we will have an int 16 for the size, like this. And all we need to do is iterate through the text and print those bytes 2 at a time. So how do we do that in the easiest possible way? There are several approaches, but I think I will just create an int32 as an iterator, and I will have an int 8 pointer as well. And I need to assert that size is bigger than 0. And what is assert? Assert is a function which checks if this predicate function is true, and if this is not true, the whole program halts. So it's quite good to use in situations like this, both in this example file, because it's easy and it doesn't matter really if the program exits, and we can also use it in our production code in some places, because we are coding a library and the programmer should send the right arguments. If not, the program should halt, I think. Alright, so we need to go into this arc4 and include what's its name? It's assert.age, and in order to get all the functionality we also need to include rnumber.h, like this. Now we'll jump down a little bit, same here. Okay, so we know that we have an input which is, let's call it input instead. That we have an input which is, which contains something. Length is bigger than 0. Okay, so let's do a loop then. So for, and we will do, let's make this an int16 instead. That will work better together with this 16-bit size. So let's, and I want to make this const as well. Same here. No. Okay, so let's set I to size and P to input. We're gonna continue the loop as long as I is positive. So I'll just put I here, because it will decrease every iteration, and it will, after a while, go down to 0 and the loop ends. And the P pointer will instead increase every iteration. Okay, so if, let's see, I need to check something out. So the first iteration, then let's say we have a string which is 32 bytes. So I will be equal to 32, and we will output to 1 byte of data. Then it will be equal to 31, and we will output 2 more. So let's see. I think we could write it like this. So if I plus 1, let's see, if I plus 1 modulus 2 If that statement is negative, so it's equal to 0, in that case I want to printf space, and in any case I will print out a hexadecimal value with two digits, and this is what we want to print out. I think this will be correct. So this basically means that if we are even, so if I plus 1 is even, then we will put the space. And we will also use our macro f, so it will print this. No, we don't need that, by the way, because we will end this with a new line anyway, so that will flush the buffer. This should be all, I think, unless I have forgotten something, but let's try it out. So what can we try it out on? We don't have all these functions yet. So let's comment this out, and this as well, and this is okay. And what shall we print as an example? We can print the key. So print bin, that's actually not binary data, but it will work the same. So we will print the key, and S key is the size. Return 0. Something like that. Let's see if this compiles, or if we need to remove something else. Like a lot of warnings. Type def unsigned sure expected before unsigned. Before unsigned. I have an empty struct, that's probably it. Let's just put something temporary here then. Type def unsigned. Maybe it is because of the position. Sometimes you need to do one thing before the other, etc. Ah, forgot to end the struct with a semicolon. Is it still complaining? Type def unsigned char int 8. If we add our type def for our struct, does that error as well? Type def struct as arc4. It's not uploading. Okay, I got disconnected. One good thing with Sociopath is that if you reconnect like this, you don't have to do anything else. It remembers and continues to serve all of your files. So that's good. Okay, let's say this again. And this one. And let's jump down a bit, clear the screen, and let's make it again. Okay, finally. Pointer targets in passing, argument 1 of print bin, differ in signedness. Okay. So this is what happens if I don't use my int 8 everywhere. So where did I not? Here. Let's just change it to int 8 and everything should be okay. Okay, we're down to one screen of errors and warnings. Almost. Does it still? Seems like it needs a typecast because the strings are generally not like these static strings inside of the code. They are generally not unsigned. So let's do a typecast int 8 pointer, and same here, int 8 pointer. Key. So strlen needs it as well. I could just make these strings signed, but then I would have the same problem in the other end instead, because the encryption standard requires them to be unsigned. So let's just typecast this as well, int 8 like so. Do we use them anywhere else except our own functions? Printf shouldn't care, right? Let's do it just for the sake of it. Int 8, like this. Okay, let's try it again. At least we have very clear and precise error messages in C. Did I go too far? Make, clean, make. S key equals S. Didn't I save? Save. Why does it? Okay, it's higher up in the code. Right. Int 8 star. And there we have it. Okay. That should be all right. Make clean, jump down, make. What does it say this time? Pointer targets in passing argument 1 of string length, difference, different. I did it in the wrong direction. Okay. That's kind of funny. So instead of int 8 here, let's see. There, and there. We should just have char, because we have them as int 8, but the functions we're calling requires them to be regular strings. So assign char pointer. Okay, this time it should look a little bit better, I think. Make clean, jump down a bit and make. Warning, pointer target in assignment from char to int 8, aka unsigned, different sign does. So it doesn't seem to be enough by doing it this way. Okay, let's do it the other way then. I will undo until I see this change, like so. So now all of these are okay, and this will probably not be, but here we can do a conversion in the other direction instead, and that should be all. Make clean, jump down, make. Okay, now we're talking. Warning, unused variable. That's an annoying message. If I don't want to use my variables, I don't use my variables. But okay, so let's do something like key equals from equals encrypted equals equals decrypted equals key equals 0. Is that enough? Maybe I should end it with a semicolon. Operation on key may be undefined. Variable as text set but not used. Right. So it wasn't enough to mention the key twice. This is only set and all of these are used. So we need a key. What about from equals key? Okay, now what? S text. But that's an int, right? Yeah, I haven't used that yet because we haven't gotten that far. These are only warnings, by the way, but when I try out my code, I want to remove everything of the sort. So which is this? This is the S text. So we will change the key later on. Let's just do S key equals S text equals 0. Now it should be completely warning free, I believe. No, one more. Warning unused variable arg4. Okay, I haven't used that. I can just comment that out for now. Make clean make. Okay, finally. Let's see if this works as intended. Example. Okay, so shall I compare the to summer's day, and then I am showing some of the key, but I am showing half a group here and half a group here. What will happen if where is it? If I just do I here. Okay, now it looks good. It prints out in hexadecimal characters in nice formatted group. Very nice. That means we can begin with the actual encryption code now. Finally. So let's go over to the arg4.h and begin working on our structure. This will contain the internal state of the encryption engine, so to speak. So let's go to that wonderful Wikipedia article. So arg4 wiki, and I want the English-speaking Wikipedia. And let's hide this and make it a little bit bigger for you guys. And let's do something like this. Let's use the whole screen. I will probably be looking at this anyway. So there's a lot of text here, and some of it are warnings that this encryption standard isn't secure. But I have read through all of that, and I'm not sure if I agree, actually. Well, the thing is, they claim that the output of the encryption is distinguishable when compared to purely random bytes of data. And that could be potentially be used to backtrack and crack the encryption. And it has indeed been used. For example, the Wi-Fi encryption standard WEP used exactly this encryption with very small keys and a special kind of seeding algorithm, which they were able to crack it in the wild in a couple of seconds. But that's only in combination with the WEP technology. And there has been some talk that in combination with the TLS, the encryption standard on the web, it's also not safe, and it's not safe the first couple of bytes which it produces is not safe. So, since we are using this encryption firsthand in our own code, not together with anything else, and I will also create a mechanism which will disregard the first 500 million output bytes, which will stop all the other cracking techniques. So I think with a big enough key, which is randomized in a secure manner, I think ARC4 is still secure. Okay, so you don't need to read through the whole shebang, but those gray information boxes are very good. So there's two steps. Step one is what I call the initialization of the crypto. That's when you only take the key and you prepare the internal state of the encryption engine. And this is what you do. And then the next stage, which happens every time you need to encrypt 1 byte, or more exactly, produce 1 byte of key stream data. So then you do this. So let's start writing. No, let's begin by creating our ARC4 struct. I will zoom in here a little bit, not that much, temporarily, so we can have both on the same page. So if we look through this, what do we need? We need an 32-bit, or we need an 8-bit int, which will go from 0 to 255. We will need an array called S, which will be consisted of 8 bits values and 256 of them. Then we have the j value, same as I, 1 int, 8. And then we have the key. And that's basically it. So let's summarize. We need int I, int 8, I, j, and later on we will need a k, so I'll put it here. And then we will need the array, so int 8, s, and 256 of them. So we have I, we have j, we have the k, and we have the s. Do we need anything more down here? We need temporary variables as well, but I won't put them in the struct. So okay, this is all we need for our own structure. So let's begin writing on our initialization function, and this will let's copy this whole thing. Let's include our arc4.h. There's something weird going on with the caps lock. Include arc4.h. I wonder if you can disable the caps lock. I never use it anyway. I use shift. Okay, let's see. Include arc4.h, and then we will do the initialization function. So it will return an arc4 structure pointer. And the first argument is the key. The second is the size of the key, like so. And the first thing we need to do is allocate space for the actual structure. So I will create a pointer for that. I'll just call it P because we're going to reference it quite a lot. And P should be equal to Malloc, and it should be the size of struct S arc4. So the size of our struct, that many bytes of memory we shall allocate. And here I will do an if clause. So let me just check the return values for Malloc. Man2, no, man3 Malloc. So I know it returns the memory address, but if it fails, return value. They return null and they set error none. Okay, so let's just do something like assert p error number, then it will check if this has errored out, and if so, display an error message and quit. Because if you can't allocate memory for our structure, there's no point in continuing the show. Okay. So now that we have allocated our structure, now I will just do this. And I will work in the following manner. Let's close this down and change up the size a little bit. And then I will paste this in and make block comments out of it. I think it's command this or control this. Let's do something like this instead. Annoying. I never seem to learn VS Code for Mac. I know all of these different things on my PC, but it's not the same on my Mac. Well, this works too. Okay, so now I have in the comments what needs to be done, and then I will just do it. But before we begin, I want to zero out all the state variables. So let's do something like no, let's just do simple thing. Int 8 x and 4 x equals 0, x less than 256, x plus plus, and we want to take the PS, so that is the this array. I want to zero that out. So PS of x equals 0, and then I'll just do PI equals PJ equals PK equals 0. I like starting from 0 instead of randomness. Okay, so the first thing is this loop right here. We'll iterate through 0 to 255 with this I variable, and we will set S of I to I. Pretty simple stuff. The code will look kinda difficult though, but it really isn't. Why is this not? Oh, never mind. Okay, so for P I equals 0, pi less than 256, pi plus plus, and ps of I equals I. Okay, this is done. So if we do one thing at a time, it's quite simple to do this actually. Can't say that for every crypto. And then we will set j to 0, but we have done that already. So we will jump into this loop and we will let the I variable do another identical for loop. So let's just copy this line. Like this. And what will happen then? We need two temporary variables as well, by the way. So we need int 8, I will call them temp1 and temp2. And I want to 0 them as well from the beginning. So let's just do temp1 equals temp2 equals 0, like so. Okay, so what will happen inside of this loop? Let's remove the things we have done already. Okay, so this is a rather difficult line. I want to break them down. So what's the first thing that happens right here? Well, the parentheses is evaluated first. So let's set, let me see, key I mod key length. Actually, let's evaluate this first. I mod key length. So temp1 will be equal to key. So it will be key of I no, where am I? We are here, right? So I mod key length. So P arrow I modulus key length. So that's the size. Okay, so this part is okay. Now we can take the rest of this parentheses one at a time. So Pj no, temp2 equals Pj plus Ps of I plus key of, and then the stuff we evaluated right here. So key temp1. And then we will set Pj. So now we are doing this part. So Pj should be equal to everything in this parenthesis, which was temp2. and mod 256. Modulus 256. Like this. And finally we should swap the values of s of I and s of j. So let's set temp1 to ps of I. No, not just I. We need to change those occurrences to pi. And pi. There's a lot that can go wrong here, as you can see. You need to be very precise. So temp1, and that is why I could do everything in one line if I want to, but it's very error prone, and that's why I break it down with these temporary variables. So temp1 is equal to ps.pi, and temp2 is equal to ps.pj, and then we will just swap them. So ps of pi equals, and here we see that temp2 equals this. No, temp1 equals this that I'm working with now, which means it should be equal to temp2 instead. And then we have ps of pj which is currently equal to temp2, and it should be equal to temp1. And that's it. The code is very difficult to read, but it's quite simple, and it's quite easy to follow it step by step if you break it down into smaller steps. And that is basically it. I'm gonna do one more thing though, because if we go back to the Wikipedia page and we go to the next step, we see that they zero out I and j, and then they have an endless loop which happens every time you encrypt a character. So we have a function which encrypts a character, which means we only have to worry about this. But this part we should put here in the initialization function, because then we can just do several consecutive calls to our arg4byte function. So p of I equals p of j equals 0 like so. And then we just return p. I think we did it right. If we go back here and we remove this line and put this line back, then we can print, instead of printing the key, let's print let's print arc for s. So the initial state of the encryption engine, and I will put one of these on top as well, so we may see the difference. No, sorry, can't do that. We haven't initialized it yet. But okay, let's see what happens. Clear, jump down a bit, make clean, and make. Okay, couple of errors. If we go to the very beginning, warning suggest parentheses around assignment used as truth value. Well, I want to use it as a truth value. I don't really care for warnings like this. If I want to code it this way, I will code it that way. Implicit declaration of function assert p error, okay. And here I forgot something. And arc4 has no member named s, okay. So a couple of small typos. If we begin in the H file, I guess this is the problem. Is this a big S or small s? It is a small s, so why doesn't it have a member called s? Did I perhaps arc4 p? That's weird. Maybe it's something because of this. We should check if x is less than 256. So that was an easy one. And what else? Assert p error. Where is that located? Man 3 assert p error. Okay, I need this GNU source thingy. Let's try it again. Make clean, jump down a bit, clear, and make. Boom. Okay. Int 8, IJK, unknown type name. Unknown type name, int 8. I put this before these. Let's move them. Like so. I don't like I have to break this up, but what can you do? This is just a warning. Error I undeclared. Okay, I missed one. Line 18. Wrong file. 18. So this should be PI, and this should also be PI. Okay. What now? Error arc for undeclared. No, the problem must be higher than that. Arc for undeclared in example. And pointer targets in passing. Arc for init key. Char star. That's weird. Didn't I use my int 8 for that function declaration? Let's check it out. So int 8 key and int 8. That's weird. Let's put this back, by the way. And okay, it's this function. Int 8 input. Int 16. Well, where is it? Let's check it out again. So, expected int 8. Arc for init key. Pointer targets in passing argument 1 of arc for init differ in signedness. Because this is a char. Int 8 key. So key is a char. Okay, let's typecast it then. Where do we have it? It's right here, okay. So it's currently a let's see. It should be an int 8 pointer. Like so. Okay, let's see what we have. Still a warning about this one, but that's nothing we can do anything about. Undefined reference to arc4 init. We need to link that one. Let's just no. So go into the make file, and then we will do. Let's make it easy. I will just do arc4.so as one of the input arguments. So make clean, clear, jump down a bit, make, and now it still doesn't compile. Undefined reference to arc for init. What did it run? GCC arc4.so. Arc4 init. Do I include it in the header file? Include arc4.h. Include arc4.h. arc4 init. Undefined reference. Okay, for the time being, let's cheat a little bit. I will fix this later on. I don't have the patience right now. So I'm gonna go and when we compile final program, we do arc4.o instead. Like so. Okay, this time it worked. We probably need to explicitly export the functions when we use the shared library. I will dig into that in a little bit, but now we do have ourselves a binary. So let's try it out. That doesn't look very good. Let's do ltrace-f Malloc arnom location. Let's try the strace. Right, initializing encryption. How did I write that if clause, by the way? Maybe I reversed the conditions. Let's see. If p malloc. Okay, this should be the other way around. So if p. Alright. Make clear make, and we run example. Did it remove everything when I did make clean? Arc for CHC. Yes. So how come it freezes there? Malloc size of struct s arc4. If that is 0, assert p error. For x equals 0, x less than 256. I think that 0 means that it's some weird number format. Make. Okay, no errors at all, no warnings even. But the same outcome. What is this? Do we have an endless loop on our hands? That's probably the only possible thing, right? So pi equals 0, while pi is less than 256. Maybe we should do this with a little bit bigger structure. These could be int 16s instead. We're probably overflowing that 8-bit variable. So that wasn't the case. For x equals 0, and what is x? X is also an int 8. So that should be the same problem then. Right. There we go, finally. Okay, so this is part of the internal state of the encryption. Okay, so the next thing we need to do, that is creating the arc4byte function, which will create one single byte of the key stream. And the key stream is what we will use to encrypt and to decrypt stuff. So let's begin. I will have int 16s with temp1 and temp2, just like before. And we do need an argument, by the way. We need to attach the structure. So let's alter this and put in the arc4 star, so we can have access to the internal state of the encryption. And just like before, I will go to the Wikipedia page, and this time I will copy this part. So in this pseudocode right here, they use a while loop, and they loop as long as it's generating output. But we'll not do it like that. Instead, this function will be called each time we will produce 1 byte. So we don't need this loop. That will be handled in the encryption function. So let's do it like before and take one line at a time. So we will do pi equals, and then pi plus 1, and we mod it with 256. First one is done. Then we do similar with the j part. So pj equals pj plus ps of pi. So we just replace the variables with our variables inside of the structure, and we mod this with 256, just like before. Okay. Then we will swap the values. So this is like we did previously with the initialization function. So I will let temp1 equal ps of pi, and temp2 will equal ps of pj, like so. And then I will just I missed the s right here. And then I will just do ps of pi equals something, and ps of pj. ps of pi, ps of pj equals something. Okay, so temp2 equals the j part, which means it should equal the I part now. This equals temp2, and the pj should equal temp1, like this. And then this one is done as well. Why did it mess up the indentation? Never mind. Okay, and then we have this t variable. That is their version of our temporary variables. So we'll just continue as before. So temp1 equals, in the parentheses, ps of pi. So this is not really a spectator sport. I hope you don't find this too boring, but we're almost done. Plus ps of pj, and then we mod it with 256. And then we use the k variable for the first time. So p.k equals p.s of temp1. And this is the final output byte, as we can see right here. So let's take care of these indentations. And then at the end we just return pk, like this. And then we have our arc for byte function, which is the most important in this entire project. So the next step will be to implement the arc for encrypt, and this is quite straightforward to do now that we have a arg4 byte function. So let's see, we need one more argument. We need to include the arg4 structure. So, or do we? Yes, we do. arg4 star. And we go here and do arg4 p and int 8. This will be the what shall we call it? The thing we need to encrypt the clear text. Let's call it CT for clear text. And int 16, this is the size of the clear text that we want to create. And we'll return this as a as a char buffer, a regular string actually. So let's create a int 16 which will hold the amount of memory we need to allocate. So let's call this mem size. And we will need exactly as much memory as this size plus 1. Okay, so we don't really need to, because when you encrypt something, if we encrypt ABC, the resulting ciphertext will be something like this. It will be the same number of characters, which makes it quite convenient for us. We don't need this variable. Instead, we'll just do, let's create a variable first. So let's call this ciphertext. And let's call this clear text, because both will abbreviate to CT and we can't mix those. So int 8 ciphertext, and ciphertext will be equal to int 8 Malloc, and we want size plus 1. Size should be enough really, but I like allocating one more just in case. We will also need something we can use as a counter. Let's call this int 16x. We will do a for loop where we set x equal to 0 and we're gonna loop as long as x is less than the size and x plus plus. And what are we gonna do at each iteration? Let's create a, let me see, we need this and that. Okay, let's do it like this. So the ciphertext of x will be equal to the clear text of X, and then we take this symbol, and some people usually mix this up with the power of, but this little symbol in C means XOR. So XOR is a binary function, like if you have two zeros, the result will be 0. If you have 1 0 and 1 and a 1, the result will be 1. If you have a 0 and a 1, so the other way around, it will also be 1. And finally, if you have two zeros, it will be 0. So that is what XOR is. It's usually used in conjunction with the key stream that a stream cipher like ARC4 produces. So here we will just call ARC4 byte with our P, and that will return 1 byte of key stream, which we will XOR with a clear text, and that will produce the ciphertext. And let's do an error check here as well. So if ciphertext is 0, then we want to assert P error R number, like so. And if everything goes well, we will simply return our new buffer ciphertext. Quite simple, straightforward encryption function. And we need a decryption as well, but that we have already defined because it's the same function, just that we give it the ciphertext instead of the clear text. And the key is the same, so basically this part is the same. Okay, so that is done as well. And before I forget, let's see, encrypted equals ARC4. So we can take this back now, and we encrypt the clear text, and we print out the encrypted. Sorry, this should be the size of the text. This should be the encrypted, because this time we don't want to check the S variable in the structure. We want to see the actual encrypted text. Yes. Okay, so after we have printed the text, what do? Do we just use the decryption function? No, we can't do that, because in order for everything to be the same, we must uninitialize the ARC4, and we need to reinitialize it with the key again. So we start everything from scratch, and then we can start to decrypt. otherwise it won't work. So let's create our uninit function as well, and that can be a void arc4. Let's make it easy for us for the time being, because there's only one thing we need to do at the moment when we uninitialize, and that is to free the memory allocation. So let's define arc4 uninit of x as free x. I will also need to find, let me just do a fast googling after export C shared library function, because there's a special string we need to use to export the functions. Let's see. This one. So let's make a definition. We define a keyword named export, and it will be the same as this. So all the functions that we want to export, like the arc4byte function, we don't need to export that because the end user will only use the encrypt and decrypt functions and the init. So we put export for this and before this, save, and we need to do the same here. So export, and not this one, but this one. Export. Like so. Okay, so that is done as well. Now we may continue our example. So we have printed the encrypted strings. Now we're gonna uninitialize. So we do arc4 uninit on the arc4 pointer. Then we repeat some of the steps like before. So let's copy this part for init. There we go. And let's create another one of these. Encrypted. So I will copy this part. Look for init. Okay, something like this, and let's put the arrow 1, 2, 1, 2 like this instead. Okay, so we initialize and we need to change the order of these. because we need to decrypt this first. So it's initialized. Now we will create our decrypted. So decrypted equals, and we will use the decrypt function, but as you know, it's the same. The only thing we're going to change is the from. Here we had the clear text before. Now we will do the ciphertext, which we get from this encrypted call. So where were we? Decrypted equals, and this should be encrypted, and everything else is the same, and this should be decrypted as well. And then we don't need to print the binary. Okay, so if we have done everything correct, then the decrypted text should be exactly the same as what we had from the beginning. So we take the text, we encrypt it, and we decrypt it back to the start, so to say. Okay, let's save, and we make clean, jump down, we clear, and we do make. Okay, not a lot of errors and warnings. Let's start from the beginning. Error t undefined, size plus t, text 54 in arc4.c. 54 ciphertext size plus t plus 1 should be plus 1. Okay, we got more errors. Let's do make clean first. Make. Okay. Warning, this for clause does not guard for x equals 0 while x is less than size x plus plus. X equals 0, x is less than size x plus plus. That shouldn't be a problem. This state doesn't guard this statement and return ciphertext. But the ladder is misleadingly indented. Okay, so it even checks my indentation thing. But sometimes that's good, actually. I have corrected errors in the past because of that. So let's see what it says. Okay, it's this part. Let's move it here. We make clean, we go down, and we clear, and we make again. Okay, passing argument 1 of encrypt from incompatible pointer type. Arc4 encrypt from. Okay. Let's see. arc4 encrypt from encrypted equals arc4 encrypt from, and from is set to this. Okay, we probably need to typecast this then, but it worked before, right? Oh, never mind. int 8 star. Let's do it like that. Do we have any more occurrences of the same? Decrypted. No. Okay, let's try again. Make clean. And make. arc4 encrypt from incompatible pointer type. Encrypted equals... wait a second. I forgot to attach the structure. Right? We did change the signature of that function. So, where were we? arc4 encrypt. The first argument should be the arc4, like this. And same with the decrypt. So, arc4. And we need to add a variable to the macro as well. So x, y, z, x, y, z. Like so. Let's try again. Make, clean, clear, and we make. And we have this signedness problem again. So encrypted equals arc4 encrypt. arc4 encrypt. So let's see. So encrypted, how did we declare encrypted? Okay, let's move this to its own instead. Decrypted. Decrypted as well, I think. So int 8 encrypted, decrypted. And we make clean, and we clear, and we make. Okay, almost there. Another, okay, that's our temporary assignment. We don't even need that anymore. So let's just remove this part and this as well. Save, make clean, clear, and we make. Okay, it compiled. Let's see what happens. Okay, initializing encryption done, and then it shows the string that we want to encrypt, and it shows the hexadecimal version of the encrypted text. Then we reinitialize, we feed it with the ciphertext, and we end up with the same string as we had from the beginning. So everything works. The only thing we should add to this, that is the, remember when I talked about some people think that the arc4 encryption is not safe. one of the biggest concerns was that the first like thousands of or millions of bytes is not good enough, so to speak. So we need, when we initialize, we need to, like, I call it to whitewash. We need to whitewash away the first like 50 or 500 million of these. Yeah. So let's go into our encryption function. No, our initialization function. This one. And I want to create an int32, which I'm going to use as a, well, I'm going to use it for a for loop, basically. I don't really want to call it I, because that makes it interchangeable with this pi. So let's just call this C for count, N for number. N is good. And let's go into the, let's see, arc4, and we create a macro for this. So we define arc4 whitewash, and we need a, we don't need an argument actually. And what we're gonna do, by the way, we do need an argument. Let's take the variable for the loop as an argument. So the only thing this macro will do is a for loop where we go from x equals 0 while x is less than let's call it whitewash count, or whitewash, let's call it m's. So these are millions of iterations. So x is less than ms times 1, 1, 2, 3, 1, 2, 3. And I plus plus. And the only thing we need to do is, okay, we need one argument more. The only thing we're gonna do, let's do it on the next line. We will call arc4 byte with the structure or a pointer of the structure as an argument. So basically that. We will call this, which it will generate a byte, and each time it loops it will do that. But we're not going to do anything with that byte, because all we need to do is getting ahead in the, well, in the state, so to speak. But if we do it like this, then GCC will recognize that it's redundant, and it will, as part of the optimization, it will just remove this. So we will need to typecast this to something called volatile int8, like so. and that basically means in this context that the GCC should not optimize it. Okay, so let's put this as part of our initialization. So when we are done with the rest of the initialization steps, at the end here we will simply call the arc4 whitewash and specify our variable for the iterations and the name of our structure, which is P, like this. Okay, and if this works, we should see that it takes longer when we run this initialization, a couple of seconds. We also need to define the m's. So how many million iterations should we have? And I want 500 million. I think that ought to do it. If you think it takes too long when you run this, try changing this to 250 or 100, because I have a quite fast CPU, so this should go quite fast. And we save everything, and hopefully we haven't introduced any additional errors. Make clean, and we clear, and we make. Yes, we did. Okay. What does it say? Okay, I++. That's wrong. Where were we? Here. So it should say X++, right? Alright, let's try it again. Make clean, go down a bit, and we clear, and we make. It compiled. Let's run it. Initializing. And as you can see, it takes a couple of steps, and then it does the same as it did before. Only this time it's probably safe. As long as we have a really good encryption key, which we don't at the moment. At the moment we only have, in this example at least, we only have the word tomatoes. We should randomize a 2048 bits key if we were to use this in the wild. But everything works exactly as we intended it to. So we have successfully implemented the arc4 crypto, and we have turned it into our very own library, which can be shared between different applications. And when I create a project for transferring and encrypting files, I will use this library for that. So then I will show you how to use this library in your code. But I hope you enjoyed this, and don't forget to subscribe if you like this and want to see more. There is a lot of advanced C videos coming forward, so don't miss out and stay tuned. Thanks for watching, and thanks for today. Sup guys, welcome to today's show. Today we are going to start a new project. and I will code something called FSE. And I'm gonna wait a little bit by telling you all what that stands for, because that would ruin the surprise for next week's project. But we are gonna focus on the ending E in FSE today, and this is a file encryptor. So we have two different files. We have FSE, which will encrypt a file. You just give it a from and a to. And then we have FSD, which will do the reverse. It will decrypt the file. It will ask the user for the key. And here is the thing which makes this project interesting. At least I think so. The program will be able to say wrong key. If you type the wrong key, the program will be able to detect that. And if you type in the right key, the file will be decrypted accordingly. So why is this interesting? That's kind of self-explanatory, isn't it not? Well, it's not very easy to do, because if we're using the encryption that we did a couple of lectures ago, when we wrote a project called R4. If you missed that episode, that was an episode about an encryption library, which uses the RC4 stream cipher. And it doesn't matter if you haven't seen that episode yet. You will still be able to code today, but you will need to link that the library when you compile. So let's say we have a program that looks pretty much like this. We give two arguments, two files, and we supply a key which is not being echoed to the terminal, and we just use the arc4 to decrypt the file. Then it will not fail if the key is incorrect. The only thing is it will produce the wrong output. So the output file will be a lot of random garbage, basically. And if you provide the correct key, it will be the right file. And that makes it very difficult for checking if the key is correct, because the program does not know what kind of a file this should be. It could be a regular ASCII text file, like in this case, but it could also be any type of binary data, like a MySQL database file or anything really. So it's impossible for the program to use the output file to see if it has worked. You could do some form of analysis and have some kind of fingerprint database for different file types. I think there is something with relate to MIME you could use, or there is also a Linux command which is I think it's just you type file and the name of the file. I think that is it. But that is not 100%. It doesn't know every format out there. And even if it correctly identifies the format, there is nothing that says it can't be two different files with two different keys with different contents of the file but the same format. So that is doomed to fail. The only way to be able to do this will be to include the key somehow in the input file. Okay? But there are a lot of pitfalls when you try to do something like this. Because if you make one wrong move, you will either make the encryption very easy to crack, or it will be worthless. Okay, so how can we go about this? Well, one way would be to, let's say this is the file contents, the clear text file contents, and let's the thing on the right be the ciphertext. So CLCI, and this is not even relevant for us right now, because the decryption tool will only be dealing with the ciphertext file. So let's focus on this one instead. So what can we do? Well, we can take the encryption key and put it in the beginning of this file in the clear text. So let's say if the key is tomatoes, then we put the regular ASCII string tomatoes at the beginning of the file. And then we either have some kind of separator. Let's say we have a double pipe sign, and then the actual file contents start. That's one way. But we are talking about the ciphertext. This is an encrypted file. So if we have the key in clear text inside of there, it would be a problem, obviously. We could, however, still keep the key right there, but we encrypt it. So basically we just add the key in clear text to the source file at the beginning, and then we encrypt this, and then we continue on encrypting the rest. And of course this is more secure than the first option, and this might be kind of tricky to crack, but we will most definitely open it up for making the security less than if we didn't have the key right there. And we don't want it. The task is to make this possible, but without in any way making the encryption less safe and easier to crack. So, and why is this decreasing the security? Well, when you try to crack something in encryption, you want to have small pieces of information.
well, actually you want a big part of information if you can get it, but basically cracking depends on you looking for weaknesses, looking for patterns in the algorithm, in the output, in the way the key is generated, in the way you do random bytes, etc., etc. And if the coder does something wrong, it gives the cracker information, and every zero or every one of information that they obtain will make it easier to crack. It will lower the possibilities, because a cracker usually it makes a computer test every possibility according to some scheme. And if you have parts of information, then you don't need to crack every combination. You can leave something out. And this can also lead to more information because of other small bugs, etc., etc. So if the cracker knows that the beginning of the file, and we know how big the encryption key is, it's somewhere between 1 to at most 2048 bits. So in the first 2048 bits, we know that the key will be stored, encrypted in the same way as the rest of the file. And this is a lot of information, and it's a very, very important information. So this will most definitely lower the lower the security of the encryption suite. Okay, so this is not a valid way to do things. Let me just clean this up a little bit. Okay, so what else can we do? Well, we can take this. Usually you don't store passwords in clear text, not even in an encrypted file. What do you do with them? Yes, you create a hash. A hash is a one-way encryption between quotes, because it's not really encryption. It's hashing, but you can describe it in one sense as a one-way encryption. So if we take our key, for example, we can turn it into a string of bits. And no matter if you obtain this string of bits, you cannot go in the opposite direction and reobtain the key. The only thing you can do is, if you try out a password, for example, then you can encrypt it the same way, and then you can look at both results and see if it's the same hash. That's the only way that you can use a hash. So let's do that. Let's select a hashing protocol. It will probably be some of the SHA hashing algorithms. There is SHA1, and there's I think 128 is one of the more secure. I need to check up on that. But one of these SHA ciphers, and I don't know exactly, but this probably means that it's 128. But anyway, let's say the first 128 bits of the file will be that encrypted hash. Well, that makes it better because the SHA hashing algorithm is most definitely stronger than what we had before with just arc4. Okay, but this is still not good because of the same reason as the last time. If we do this, then the crackers will have absolute knowledge of the first 128 bits of the encrypted file, even though it's hashed, and they won't be able to use that per se in order to turn it into an encryption key, but they may still use informational parts of it in order to crack the cipher in other ways. So we don't want to do this, but we still want to use the hashing algorithm, SHA. But where do we store the hash? What if we put it on line 5 or something, a couple of characters in? Well, we still would have the same problem because it's an open implementation. The crackers will still know where this will be found. So we need to store it somewhere in this file, but different places every time. How can we do that? And how can we find it the next time? My idea is when we encrypt a file, the first thing we do is we produce a random value. Let's take a new page. So first we do a random value of 16 bits. That will mean a number from 0 to 65,535. And I will not use a 0, so this will be 1 to 65,536, I think. I haven't decided that, by the way. Let's do 0 for now. Okay, and where are we going to put that number? Well, first of all, we're going to put that random number. Let's call that the offset number. Yes, this is the offset. So the first 16 bits will be an offset. But now you might go, wait a minute, isn't this the exact same problem like we had before? That the crackers will know exactly what this part of the file will be. Well, will they now? First of all, this is a cryptographically secure random value, which means it can be anything between 0 and 65,535, which makes it 100% impossible to do anything with, because you cannot turn it into something else, you cannot reverse engineer it in any way. So this should be secure. And what do we need this number for? Well, let's say we randomized the number 650. The next step will be to produce 650 encrypted random bytes. So the same cryptographically secure way that we created this random value, we will create a padding. And that will be somewhere from 1 to 65,535 bytes this time. Of random data. Which means that this offset will be exactly as secure as this offset thingy. Let me color this in. So the offset will be this yellow part, and then we will have our padding. Like so. That's the padding. Okay, and what comes next? You guessed it. The hash. And let's color the hash green. This is a little bit smaller. Maybe like so. And the rest, let's make that this color. This will be the actual data. And in this example, this looks like the data part is very small in comparison with the other, and it might be if it's a very small file, but more probable is that the next like couple of pages will be the data. So the data can be like several gigabytes. It can be any length, and then we will encrypt everything. So let's do something like this. So even the random data will be encrypted as well, and then written to the file. When we go the other direction, when we want to decrypt this file, well, then the program will ask us for the key. When we input the key, we will initialize our encryption engine with that key, and we will begin by decrypting the first 2 bytes of the file containing the offset. And now there's 2 possibilities. Either we have the correct key and we get the correct offset value, or we have the wrong key and we get any random number between 0 and 65,535. Oh, and let's say we did get it wrong, the wrong encryption key, and this number is, let's say, 30,000 or something. What we'll do is we will skip the next 30,000 bytes, but as we pass through it, we will decrypt this data as well. And that is so the internal state of the encryption engine will be correctly correct when we will start decrypting the real data. And then we are at place 30,000, where we believe that the hash is located. We can't really see if there's really a hash there, because the hash won't be in any ASCII format. It will be in a binary format, taking up like 128 bits in this case. So we will read that data. We will read the wrong hash and compare that to our wrong password, which will not work. And then we can say wrong key. For it, in order to, and then the program terminates. For it to really work, we will have to do this again with a real password, the real key. So let's say we have the real key this time. We will decrypt the first 2 bytes, and we will get the correct offset of 650. We will jump past these 650 bytes, but we will decrypt them one by one as we pass them by. Then we will take the next 128 bits, which we think is the hash, but maybe not. Then we will encrypt our key with, we will hash our key, and we will get a hash back. And this hash we will compare to this hash. And this time we will succeed. So we can tell the user correct key decrypting. And then we will decrypt the rest of the file 1 byte at a time, all the way through, and we will write only this blue part to the file, discarding the offset, the padding, the hash, and only writing this blue, which will be clear text data. So this is my idea, and I think it's gonna work, that it's gonna be a secure way of using the ARC4 cipher. One prerequisite is that we use the whitewashed feature from the library that I showed you last week. But those two in combinations, this way of handling the files and the hashes and the keys, etc., in combination with a secure way of creating keys. That would be the third. But most important, we will have this way of expressing if we have the right key or not, and we will have the whitewashing feature to don't be affected by most of the recent bugs, etc., which has been found in the ARC4 cipher. So I believe that this is the solution to creating this ability to say wrong key if it's a wrong key without in any way decreasing the security of the encryption engine.
Sup guys, welcome to today's show. Today we are gonna code a safe string library. And what is a safe string library and why is it needed? Well, let me show you an example. So let's say we have a main, and I'm not going to do any error checking now, so I will simply take the argument. If this were production code, I would of course do a check so we don't access parameters in command line argument that's not there. Let's create a string. Let's call it str and let it be 8 in size. And then we will create, let's do just a char pointer, and I will let it be equal to hello, like this, and I will include 2 files, standard IO and the string library, like so. Okay, so I want to put this p string into the str variable. So then I use string copy, and the target is str and the source is p. So this will copy the contents of p, i.e. this hello, and put it into our str. And then I will simply printf this str like so, and return 0. Okay, let's compile this. And we run it. No problem there, right? Sorry, I'm gonna use nano today so you get syntax highlighting. Okay, so let's instead, well, let me do like this. if argc is less than 2, return -1. Just a simple check. And we're going to take one argument from the standard input. So instead of doing p equals hello, I'm going to do p equals argv1. So we take the first command line argument. We compile again. And if we run it without any arguments, nothing happens. What if we were to do the hello string again? Then it shows. But what if we were to do something bigger than 8? Like this. Segmentation fault. The program crashes. Why does this happen? Well, these variables are placed on a stack. We only have room for 8 characters in this variable. So if we copy a lot of those with a string copy, it will start to overflow the stack. So basically it may overwrite variables. In this case though, the str is on the top of the stack, so it will start overwriting other things like return addresses and saved stack pointers and other important stuff, which basically means that the program will not know how to return from this function, and it will jump into some memory address which is not right, and it will crash. So when you're dealing with strings, a lot of the work is to make sure this doesn't happen. One possible solution to this is that instead of using the string copy like this, you add an n in the middle, so it's string n copy. Because then you can add a third argument, which is the biggest number of characters to copy. So if I put 7 in here, it can never copy more than 7 characters. So let's try this again. Hello, it still works. And if we do this, now it will only do the first couple of characters and then exit without an arrow. So if it's this easy to fix this problem, why bother with it? Why make a video about safe string library? Well, this is only one example. A lot of the times you don't use functions like this. You edit the strings yourself. Or what if you need to read all the lines in a file, for example, and put it inside of a string variable? How would you do that? You need to allocate and reallocate memory so you have the correct amount of memory all the time. So it's not that straightforward to create a safe library for this. Okay? So my plan is to make something that will work like this. So let's remove stuff in here. So I want to do something like this. I want to create a string. So this is my own variable, str, and I will initialize str with some initialization function, like let's call it init, and and it will take what will it take? It will take a string to begin with. So the first string to put inside of this str variable, let's say hello, like so, and I will not use any numbers, so nothing like this, that we only need 5 characters, etc. I want to make this library as easy to use as possible. And what if we wanted to add, like, hello, the word there, so it's hello there. Then we can use a concatenation function. So we just provide the string a variable name, and then what we want to add to that string. So let's say there. And then it will automatically take care of allocating the memory necessary in order to add this to the string. And if we want to print this string to the screen, we can do this by just referencing, let's say, well, let's call it fold, and then we just give str, and it will print the contents to the screen. And then we only need some kind of uninitialization function. So let's say uninit str. So we can easily use this concat inside of a loop and read an entire file. It can be a very big file, gigabytes or even larger, and it will put it inside of this string construction. That is the plan, anyhow. Let's see if we manage to do this. I'm going to clean up a little bit here and create a simple makefile. So what do we need? We're gonna have a file called safestr.o, which depends on safestr.c, and we want to compile it using let's see, $roof or caret, or I'm not sure how to pronounce it. This means the source, the C file in this case, and this means the target, the .o. And we're going to do -c, and yeah, let's not overcomplicate stuff. That's good. And then we will have the safe string SO, which depends on safe string dot O, and then we will run cc and the source -o, and this will be the target. And now we need a couple of options, and I don't have them in my head right now, so I will use a variable which I call options, which I will put some content into later on. And when we do all, I want to first clean and then make a safe str.so. And finally I will put in the clean, which will remove all the .o files and the .so files. So something like this. So if I just do touch and let's see, safe str.c, I should be able to do make, and it creates the .o file. We do get an error here, but that's only because we have empty files. This for make clean, and it's gone. We also need a safe str.h, and I'm gonna create a new window. I'm gonna go into code and safe string. I'm gonna set my home directory to this directory, and in here I'm gonna open the .h file and .env, safe str.h, safe str.h, and in here I'm just gonna open the C file. So safe str.c, safe str.c, and we're gonna include our safe str.h like so. And as usual, I will begin by defining my main. So we'll see what I want this to do. So let's create a string which we'll call str. We're going to initialize it like before using an init function which we hasn't made yet, and we will put in hello, and then we want to concatenate the str with the word there, and Yeah, let's do something like that to begin with anyway. And then we want to uninit str, and in between we want to print it. So printf %s and fold str. Return 0. Okay, so this is basically what we want to achieve. Okay? The first thing I'm going to do is include a couple of libraries, just the standard ones. So ug std.h and stdlib.h include stdbool.h. This is quite new, by the way. You might have to install the latest part of GCC if you want this. So this adds native support for booleans. stdbool.h, and I usually include string.h, but I'm gonna wait a little bit. My hope is that I don't need that and I can write my own functions for that instead. However, I do need assert because I don't want to worry too much with error handling when I'm doing a video. And I also need to do a definition for GNU source, and that is so I get the function assert p error. So basically this function is inside of this file, but it won't be defined unless you define this one. And it's basically a combination of the assert function and the p error, the print error function, which is quite nice, I think. But then you also need to include the rnumber.h, like so. Okay, so let's define our structure, our string structure. So I'll call it s-string, and what do we need inside of this? Well, we need some kind of a counter so we know how many bytes of contents we have in our structure. So let's make this an unsigned int, and we can call it count. And we do also need the buffer, the actual string, and this can be done a couple of different ways. I could define it as a char pointer like this, and then I allocate memory to this one. But an even cooler way, I think, is to use a new function in later C versions that you can create a char array, basically a string, like what we're gonna call it, data. And usually you do something like this. So you put like 64, so it will have 64 bytes in it. But if you put a 0 in there, then you define the variable, but you don't create any space for it, which means that you can only do this at the end of the structure. So this entire structure will be variable length, and we can just increase and decrease the entire structure when we need to handle the strings, which is kind of nifty, I think. Okay, and I will type def this struct s string to string with capital S. I will also create a couple of function definitions. We have a main with an, I'm not sure if I'm gonna take any arguments, but let's put them here to begin with anyway. And what else did we say? We want an init function, and that init function will take a string, an initial string, and we want to return a pointer to a string, so our own structure, like so. And then we want a concatenate function, which will take a string pointer and another string, and this will return a bool if it was successful or not. And we also need an uninitialization function, but for the time being I think I'm going to do a macro. Perhaps I need more intricate functionality later on, so I'll change that, but for now I will just do this. Uninit x will be free x, like so. So let's start by creating our init function. So it will return a string pointer, and it's called init, and it takes a initial string, like so. And we need a size variable, unsigned int size, and size will be equal to length of str. So we do also need to define that length function, and that will basically be let's see, that will basically be, well, it will be pretty much the same as the regular strlen, right? So unsigned int length, and it takes a char, array. We need an n and a pointer. Let's do the const right here. And we'll create a pointer for n is equal to 0 and p is equal to str. We're gonna loop as long as, let's see, as long as the thing that p points to is not 0. And in each iteration we're gonna increase p and we're gonna increase n. And we don't need anything else, no body of this one. So I'll add a semicolon at the end. And then I'll just return n. And I want to create a function declaration for that as well. So unsigned int length, and it'll take a char star, like so. Okay, so now we have the length of the string. And since this is the initialization function, this will be the first string, so we don't have to think too much about it. I do have, however, one additional byte allocated, and let's allocate no. So it will be, this is how much we need for our string, but then we also need the size of our structure, which will be struct, why did I name it? S something, S string. Okay, that should be enough memory, right? So let's create a string p will be equal to string malloc size, like so. And we do also need to zero this structure. So one new way of doing that, first we need to assert that p is not 0. Then we're gonna do a, let's see, p, I think it's something like this. P equals this. I think you do it like that. Maybe we need to dereference. Let's see if that works. Okay, so we have the empty structure. Now we want to copy the actual string into there. So mem copy and into p data. We want to copy the string, and let's see, we need a variable for the length. So let's do an n as well. So n and size, and we let n be equal to the length of the string, and we substitute this by n, which means we can copy n into the string. And then we'll just return p. Okay? So let's comment these out because we're not done with them. And not this one either. But the initialization should be okay, and let's do a printf so we see that it's working. So %s and this will be str data, like so. Okay, let's see what happens. Oh, assignment discards const qualifier. Okay. So let's do length. I think it should be okay to add the const right here. Did I have the const here? No, I didn't. And init, we need a const there as well. So const basically means that we cannot write to that argument. Same here. Okay. So const, and maybe we don't need it there. Okay. Assignment discards const qualifier p equals str. Okay. We have a typo in the header file. Let's see. Main. That should be just int. And what did we do wrong here? Let's see. It's in the length function, I think. n equals 0, p equals str, p, p plus plus, n plus plus, return n. Let's see what it's. Let's see what it said. Okay, it didn't like this construct. Perhaps I need to add some options so it uses the new standard. Let's see. If we add dash std equals let me see, c2x, and let's add it here as well, std equals c2x. Still doesn't like it. Perhaps it needs the space there. Expected expression plus p equals. What if we do the slightly older standard and put a 0 in there? No, still does not like that. I think I need to typecast. That's probably it. So let's make it so, and then I do string like so. Okay, now it works. Mem copy, okay, what do we need for that? Mem cp, okay, it's side of the string dot age. Let's create our own. No, safe string. Let's see. So we have a void pointer and let's do bool instead. And we can name it copy. It's gonna take a void pointer to a destination. It's going to take a const void source and a const unsigned int n. And this function will basically be like this, but not exactly. But let's start there anyway. So const char p let's do let's do like this. So const char p p source and just char, no, not char, void. And right here we just do void p destination. And we do a for where unsigned int x. And inside here we set x equal to n. We set p source equal to source. P destination equal to destination. And we're gonna iterate until x is 0. And each iteration we will increase p source, p source, and p destination. And what are we going to do? We're going to take whatever p destination points to and set it to what p source points to. We can make this a void because not much can go wrong, and if anything goes wrong then the program will crash. So like so. Save, and we need a function declaration. So void copy, and we have a void pointer for the destination. We have a const void pointer for the source, and we have a const unsigned int, like so. Also we need to change so we use our own function. Where is our mem copy? Right here. So let's just do copy. Okay, it's getting better. Dereferencing, okay, it doesn't like dereferencing void. That's right. Okay, so let's go into that file again and let's change those pointers to char instead. And let's typecast a little bit. So P Mr. C is equal to the char version. Or the const char version. And this will be equal to the char version of pdest. No. like so. Okay, int main, conflicting types, that's right. We need to add our arguments. Int argc char argv, like so. And it compiles. It does, however, compile into a library, which is a little bit difficult to debug or to try out. So let's alter our make file a little bit, and let's change this. And this. I don't think we need to change anything else, actually. Okay, let's see what happens. Segmentation fault. Okay. Let's trace F. Didn't say much. And ltrace didn't say anything. Let's double check the code. Let's see. Safe string.c str data. So n equals length of the string. I think we need to try out our two utility functions so we know that they work. So we have our length, and we have our mem copy. Let's start with the length. And we'll check the length of A, B, C, D, E. That should be 5, right? Okay, no problem with that one. So how do we check our mem copy in an easy enough way? Let's create 2 char buffers. So buff1 16 and buff2 16, and I'm gonna string copy into buff1 low new. And I'm gonna mem copy into buff2 from buff1, and let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I'm gonna print the contents of buff2. I'm also gonna memset both of them to zero them out. Like that. And I need to temporarily add the string library. Memset. Oh yeah. Wrong punctuation. Memset. There we go. Hello, you. Okay, so both of these functions seem to work. So how come my stuff doesn't? Str equals init and printf str data. Perhaps it's about null termination. Yeah, that's probably it. So, where's the init function? How much am I allocating? N plus 1 plus size of this. So there's room for the null terminator. Let's see. If I create a regular char pointer, and char pointer should be equal to p data plus n, and that should be a 0. It should work, I think. Still segfault. Init hello. And take this string. N equals length string. Size equals n plus 1 plus the size of this. P equals string Malloc size assert p equals string 0 copy to p data the string and what happens if I remove this line? Okay, so that's where it seg faults down. Even though the copy function actually works. So p data string n, and n is the length of the string. Okay, I forgot to, I set the x to n, and my idea was to decrease it, and when it reaches 0, we're done. But I only did half of that thought. So we should add x minus minus here as well. Alrighty then. Then we probably don't need this stuff, since everything already should be zeroed out. There we go. Yeah, now it works as intended. Good. Sometimes it's those small little things that makes you have to troubleshoot forever. Okay, where were we? Safe string.c. The only thing we have left actually is to create the concatenation function, right? Which basically merges one of my strings with a regular string. So let's do that. And that is a bool. And what did we call it? We called it concat. And it takes a string pointer as an argument, and a const char source. Okay, so first we need to calculate the memory consumption, and we do need an unsigned int n, which will be equal to the length of source. So the size, we can make it in 3 steps. Let's do a current size as well. So the current size is equal to the destination strings count plus 1 plus size of struct s string. So the size of the structure and the contents, that is the current size. And the new size should be equal to the current size plus n, the number of bytes we need to concatenate. So then we have the new size. We also need a pointer, string p, and let's see. No, do we really need that? Yes, I think we do. So P is equal to string, and this time we use realloc. And the old memory segment is the destination. Yeah, it's a destination. And the new memory requirements is the size. That will be our P. And if P fails, we'll simply return false. And if it doesn't fail, then we have the memory we need. So now we just need to copy the new string. So let's do it basically like we did before. I will create an let's see. I will create a regular char pointer. And that char pointer should be equal to p data plus p count. So basically it should be equal to the old count. We need to increase by that, with that, so we come to the end of the old segment, and that's where we will put the new data. And then we will simply copy to p data, no, to cp, And what should we copy? We should copy the source. And how much of it? It should be n. Like so. And then we will simply do p count plus equals n. So we increase the count. And we return true. That should basically be it, right? So let's go down here. I will remove this temporary printf and we'll add back our concat. And right, we need this fold as well. The fold should simply return the value. Let's do it quickly. Char fold, and it should take a string as an argument. And it should simply return string data. Easy peasy. Let's create the function definition as well. So char fold string star. And we do have our uninit as well. So maybe this compiles. Let's see. Okay, what does it say? It should be str, right? Where is it? Here, concat str. There. We should add the 0 bytes at the end when we concat. So let's see. So CP should then be equal to P data plus the new P count. And let's zero that one. Like so. It compiles. Hold your breath. Almost. It showed the there, but it didn't. It overwrote our old data. I think I know why. If we go to the init function, we don't really increase the initial length. So P count should be equal to n. That's right. N plus 1. Yeah. Okay, let's try this again. Hello there. Okay, so what have we learned today? We have learned how to successfully create a safe string library with a concatenation feature and some other stuff. And I will leave as an exercise to you to create an equal function that you can use in order to check if two strings are equal. And it should work with our string data type and regular strings in any combination. If you like this content, please like and subscribe. There will be a lot of more C videos, both beginner level and very advanced. I have a lot of interesting stuff in the pipeline. So thanks for watching and thanks for today. Sup guys, welcome back everyone. Today I'm gonna tackle another of these challenges, and today I'm gonna do the one which is called Get Nextline. The task is we should read from a buffer, like from a file or from a network socket or similar, and we're gonna read until we get a new line. Let's make it simple. We read from standard input and we echo it out to standard output, one line at a time. It doesn't have to be more complicated than that, and I want to utilize the heap for this. Alright, so let's begin. And once again, I haven't rehearsed this, so maybe I'll fail. We will see. I am going to include stdio, at least for now, because I want this during development. And this is the gnl.c, get next line, like this. And since I'm utilizing the heap, we are gonna need the stdlib library. I think that's the, let's see, man3 Malloc stdlib.h. That's right. Okay, so we're gonna have a main function as usual, and we don't need any arguments for this one. And then I'm gonna have a function called gnl for get next line, and we don't need any arguments here either, because we're always going to read from the standard input. So, well, let's see. Let's start with the usage. So if we go into the main function like this, and let's create 2 pointers, P1 and P2. So I'm going to read 2 lines, one at a time. And I will just simply do P1 equals GNL, which will read the first line. P2 will equal GNL again, like this. And then I'm simply gonna print them out to the screen. So I will put them in single quotes as well, so we see that we don't include stuff and characters that we shouldn't. And I will put a new line here because I am not going to include the new line in this string. So one of these, and I'm gonna paste in like this. And then we will do P1 and P2. Simple enough, and I don't need to jump all the way like this. This looks a little bit better, I think. And then we will simply return 0. But before we do that, I also want to free these two pointers. Like this. Okay, so I'm not sure if I need any additional functions. I think we will see. So char GNL like this, and I put some enter here. Okay, so what do we need? We need a pointer P. This will hold the buffer, and perhaps we should define a maximum buff size as well. Let's say 2048 bytes. And in addition to this, this heap segment that we're going to return, I think we will use the, let me think. No, let's do it like this. Okay, so let's allocate the whole thing, because we don't know beforehand how much it should be. So we allocate everything, and then I want to zero it out. So I will need another pointer. Okay, so I'm thinking about something like this. I think I need to log in again. Just 1 second. Okay, so let's read 1 byte at a time into this buffer, and I'm gonna create one additional pointer. Let's call it S for start. So this will have the same value as P from the beginning, pointing to the first byte of the memory segment. But we're gonna mutate P, so that's why I wanted to save it in S. And now we will just do a loop where we read with a read system call, 1 byte at a time. And if we encounter a new line character. What shall we do then? Well, we should do something like this. If we get a 0 byte, then we end and return. And if we get an error, then we also end and return, unless it's the first byte. So if we don't have any other result, then we will error out. Otherwise, if we get an error, we will just return what we have. But then we come to these new lines. We do want to return when we get a new line, same as above. If we have 0 bytes read, then we will also error out some way. But what if we get a Windows style new line like this? Well, we should tackle that the same way as a regular new line, but how do we read this? Because if we get this R, we can't really read another byte just to check if it's an N. So what do we do with that byte then? So I think the best way is just to entirely skip those, so we don't use them at all. We just delete them. And I think these are all the different cases, because otherwise, if we get a regular character, we add to buffer and continue. So quite simple actually. Okay, let's see. We have a P which will be pointed to the current byte, and we have the S which is the entire buffer. So let's do something like a while loop. So while, let's just do while 1, so an endless loop for now, and then we will enter some conditions later on. Okay, so what we need to do is similar to what we did last time when I did the Printf implementation. We will have a loop. So step 1 is we read a byte from a buffer, and we need to take care of the return value. So let's just do an int r for return value, and r will be equal to read, and we are going to read from standard input, yes, and we're going to read into the P and maximum 1 byte, like so. Okay, so now we have a value. Now we can switch for that after we have checked if we did get an error. So if r is less than 1, then either the buffer is is read in its entirety, so the file is closed basically, and it can also be an error of some kind, but that doesn't really matter because we're gonna handle it the same. We also need a counter, right? I will make this an unsigned int n, and let's set n to 0, like so. Okay, so what do we need to check? We have a couple of different checks. The first is if r is less than 1, which means we are going to check how big n is. So if this errors out, and if n is less than 1, in that case we will just return 0. But if the read operation fails, but we have something in our buffer, then we will just return our buffer. Simple enough. We need to have those brackets, I think. So we don't get any problems with this else statement here. Okay, so if we successfully read 1 byte from the buffer, then we can do another check. So else if n is more than buff size minus 1. So if buff size is 100, we check that n is not bigger than buff size. We should probably do buff size minus 2 just to be sure. So if n is greater than buff size minus 2, then we are possibly overflowing the buff. Okay guys, let's continue on with our code. So the last thing we did was we began checking that the character we read fits inside of our maximum buffer size. So in case this n counter exceeds the buff size -2, and I do -2 so we have a little space there, what shall we do then? We can't really read any more characters, right? So we will simply return S, but we also need to add the 0 byte at the end. Or let's not, by the way. Let's just return a buffer, like so, and S is the start of the buffer. And instead, let's zero out the entire buffer from the beginning. So let's just do 0 and send the reference of S, and then we will create this function real quick. So we will have a function called 0, which will take in an argument of type string pointer. And return another, or return the same rather, string pointer. So let's just do it really easy. So char p, and we will just we will create an int counter, and we will just do a simple for loop. So we will set the counter to 0, and we will loop as long as n is less than the total buff size. And what shall we do at each iteration? We shall do star and p plus n. Let's do like this. So p plus n plus plus equals 0. And then we don't even need a body for this one. And at the end we simply return p back to the user. And let's make this pointer a constant, because we don't really need to change it. So something like this. So now we can be sure that the buffer is zeroed out at the start, which means we can safely return s as long as we stop before we fill up the entirety of the buffer. Okay, great. So now we have a check that we don't overflow things, and we have a check if the read operation fails. So now we can code the happy path. And as I mentioned before, we will simply do a switch statement. So let's see. We will switch P. And what shall we check for? Well, what about 0 bytes? Shall we break at the 0 bytes? Yes, I think we shall. So if case is 0, we'll just return S. Easy. And this break really doesn't make sense, but I like ending all the cases with a break. And what else? If we encounter an enter character, a Windows new line, then we will just continue, or we will break. And if we see a regular new line, we will return. Let's do it like this instead. So case 0 and case new line. Then we will return the string. And if we get a regular character, what shall we do then? We have already... Oh, wait a minute. We can't just break at this R because we have already read the character to our buffer. So what we need to do in this case is we need to reset this character in the buffer to 0. And we will not increase the P, but in this case we will increase the P. Okay, 1, 2, 3, 1, 1, 2. Okay, and we can end this if statement. If blah blah blah, else do. Okay. All right. I have probably forgotten something, but But let's test this code and see what happens. So this will be ending the while loop. And this should not be reached. Don't we all love messages like that, by the way, in the code? Because almost at the kind of Murphy's Law, you always happen to end up at this code. Anyway, so what shall we do if we reach this part? Well, let's just let's remove this stupid line and let's just return S in this case. Perhaps we should do a check of this n variable, because we are counting. We need to increase that counter as well. So let's do that here. And instead of plainly return S, we can do a ternary. So if n is less than 1, so if we haven't read any characters, then we will return, let's do it like this, then we will return, do we have any error code? We did make it a char, and in this case we return 0, so let's return 0 if we fail. So 0, otherwise we return S like this. And save. Okay, so let's try this out. We have already written this temporary testing of a main function. So we read 2 strings and we print them out. So let's see if we get any errors. We probably will. Yes. Assignment of read-only location. It's probably because of that const. Let's remove that. Because this it shouldn't be a read-only location. Let's remove this -1 stuff. Okay, let's try it again. Okay, a whole lot less errors. So passing argument 1 of 0 from incompatible pointer type. Okay. So instead of sending the reference, let's just send S. And now we only have 1 implicit declaration. So man to read uni std. Right, we don't have that, so include uni std dot h. Okay, it compiled. Warning, overriding recipe for target. Ignoring old recipe. Maybe that has something to do with, let's do make clean. Because I have my printf code in the same make file. Let's just do make get next line. Okay. What happens if we do make clean and we compile this manually? So gnl.c-o gnl. And let's add wall as well. Okay, so no problem. Overriding recipe for target printf. Ignoring old recipe for target. What is that? I have never seen that before. Printf.o. Aha! I forgot to change this when I copy pasted. This should be GNL. Make clean, clear, make. Okay, that's better. Let's try this GNL. And we need to create something which puts a couple of lines of text to the standard input. So let's just create a file. That should do it. So test.txt. This is line 1. And this is 2. And let's do 3 as well. Like so. And then we run GNL and we take the input from that file test.txt. That's what this character means. This is line 1 and this is line 2. It works almost perfectly, but as you can see, with the help of those single quotes that I talked about before, we see that we are printing out the new line, and we don't want to do that. So let's go back to this, and in case of new line, we just return S, but we should set P to 0 first, because we don't want that new line in our variable. Okay. And then we can try it again using the same command. Okay. Still doesn't work. Why is that? Did it recompile? So we read it to P. What happens then? We check if 0 or if it's a new line, and then we set P to 0, and then we return S. When do we increase? We increase down here. So we shouldn't really, we should be able to overwrite that new line, I think. But we don't. Case we are switching for P. Case N. And we are setting P to 0. Maybe we should do some kind of check. So if P not equal to S, so we should do this only if this isn't the first character. In that case, we're gonna check if P minus 1 is equal to a new line. And in that case, we set P minus 1 to 0. And we set P to 0, and we return S. But this shouldn't really happen, right? Well, let's try this, at least as a test. It didn't really remove everything when I did the make command. To make clean, remove Printf and GML. Like so. And we do the make. Okay, now we get an error. Okay, at least we get an error. And we will remove this code because it's not really something that we need to do. The compiler confused me a little bit. So this ought to be enough. Okay, no errors. We get a fresh GNL file, and then we will just run our command. And now it works perfectly fine. Very nice. Before we end, I will just test sending it a lot of different characters and see what happens. So for in dollar. Let's send 10,000 occurrences of an A to Printf. Okay, it works. Then we will take this entire command and we will pipe it into our GNL. And it doesn't crash. It takes the first 1,000 or so and print them to the screen. So what have we learned today? We have learned how to solve the getNextline challenge by using the heap and by using the read system call, which basically lets us read one character at a time in this case, and we check if it's a new line or if it's an error or if it ends, and we return a pointer to that heap area each time. So every time we issue the GNL command, we get one line returned. So that's all for today. If you are interested in this channel and want to see more, please check out the small red button at the bottom right of your screen. It's pretty small, but if you click on that one, you can easily subscribe to this channel. And if you like this video, you can also click the like button, of course. Thanks for watching, and thanks for today. Sup guys, today we're gonna do some challenges. The challenge I wanna tackle today is the Printf challenge. At least I want to start with the Printf challenge. And Printf, maybe you don't think about it, but Printf is a very, what should I say, complicated function, actually. There are a lot of different parameters and switches and different percent, etc., etc. So it would take maybe a whole season of episodes to create the entire thing. That's why I'm going to limit it a little bit. I'm going to limit it to 3 different variable types. So I'm going to do %s for string, %c for char, and %d for int. And I'm not going to use any of these switches like number of zeros or stuff like that. Only these 3. But in order to make it a little more difficult, because this has been done a lot of different times before, so I want to up the ante a little bit, and I'm going to set some limits. So I'm going to code it without any libraries, not even the standard C library. The only thing that will be allowed are the system calls. So like read and write and stuff like that. Because if that's not allowed, I wouldn't have to create the calls myself with assembly. And we've done that already. And I want to focus on the C today. So system calls and their wrappers are okay, but nothing else is. And if I get stuck, because I haven't rehearsed this, if I get stuck, no Google is allowed or anything of the sort. The only thing which is allowed when it comes to documentation is the manual pages. So the man Linux command. That is always okay. And my own libraries are also okay. I'm not gonna use a lot of those, but perhaps for one part of the solution. Okay, let's begin and see what we can achieve. So I will code inside the terminal today. And the only thing I have prepared is an empty Printf file. As you can see, it's empty. A symlink, which is called A, and that's just pointing to that .c file for convenience. And then I created a simple makefile, which will compile everything. So let's begin. And I'm going to begin by creating a couple of utility functions, because if I'm not allowed to use almost any libraries, I can't even include the std IO. UniSTD is needed though for the system calls. Well, I need to define the following utility functions. strlen, because I need to be able to count the number of characters in a string. I will also need something like puts, which works similar to printf. It puts one single string to the screen, and no format strings and stuff like that, just one regular argument. And I need that for debugging, basically. And I will also create something like, I think I'm gonna name it putchar, which will print a single character, one char. And finally I will need something like char dupe, I think I'm gonna call it. It's a function which will take one argument. Let's begin with that one so I can show you instead. So char dupe will return a string, and it's gonna take an input, which is a regular char. So it takes a char and converts it into a string. So, and this is quite simple to do. I will just create a static buffer of 2 bytes, and I will also create a pointer. Not really necessary, but I like working with pointers. I will point this towards the buffer, and then I want to change the first character to the C, and then I want to increase it so it goes to the next position, and then I want to put the 0 byte there, go back, and then I will just return the buffer. So if I send a J, it will create a buffer of 2 bytes with a J and a 0 byte and return it. Okay, so one function is done. This was the easiest one. Let's test it. We need to create the put s so we can start testing things. I will let this be a void, I think. Let's start there anyway. See if it makes sense to return anything. So put s, and we will take a pointer as an argument. str, and what do we need for this one? It's not a lot, actually. Let's see. We need to write it towards that, and we need the string length. That's right. So let's pause this one, and we will create the string length. So a string length is an unsigned integer, strlen, and we will send a string to it. I want to create some space here. I get annoyed when I have a lot of text below the cursor when I code. Okay, so strlen, what do we need? We need an int counter, so int n, and we need a char pointer, and then we can just do a for loop where we set the pointer. Let's point it to the str, and at the same time we set the n to 0, and we're gonna loop as long as the thing that this pointer is pointing towards is not 0. So we'll just do a star p, and each run we will just increase the pointer, and we will increase n, and that's it. We don't even need a body for this one. And then we return n. I think this should work. Okay, so what do we need here? We need to know the length. So unsigned int n, we set n to strlen str, if n is less than 1, so if an error occurred, or if it's an empty string, then we will just return -1. No, this is a void. Maybe it makes sense to... never mind. Let's just return void. In other case, we will write towards our standard output, and I have a memory rule which you might find useful, and that is 0 is the standard input, 1 is standard output, and 2 is standard error. So first you take the one that is a singleton, because we have 1 in and we have 2 out. And then you take the one that are mostly used, so standard output is used all the time, and then just standard error, which means that we will use 1 in this case, and we'll just send str and n. And let's, by the way, make this a regular int. Then we can do return -1 on this one, and we can return the value that write gives us. So if write errors out, our function will error out. Okay, so let's create a main real quick, where we just test our putS function. So let's do something like hello world, like this, and return 0. And we make this one. Oh, that was a lot of errors. A typo on line 16. Const. That should be a T right there. By the way, const, I don't think I have explained that. Some people who code C would have omitted const in this case, so we just have char str, and then they might, instead of using a pointer in addition to the other variables, they would have used this the same. So increase str every step of the loop, etc. But I don't like coding that way, because I think input should be input and output should be output. That makes for less errors. So I make this const, which makes it impossible to alter this argument. Then we try again, and now we do only have 1. For p equals str, warning assignment discards const. Okay. When you use const somewhere, you need to use it basically everywhere. At least if you're using, let's see, where were we? It's here, right? So char p const char. Okay. Well, let's make this const as well. And then you might think, well, we are setting this afterwards, and we are even changing this, but it works a little bit differently when they are regular variables. I think the only thing we're not allowed to do is reassign it totally to another variable. Well, we do that here, but you can only do it once. So basically like, like TypeScript. I think. I will double check this and get back to you about it. Okay, it compiled. Hello world. We have created our own strlen, our own puts, and it works almost from the start. Great. And we can't really test. Yes, we can, by the way. Let's test the first thing as well, the char dupe. So we can just do, let's do it like this. We create a pointer and then we just do p equals char dupe and we'll send an x, and then we just put s p. We need to start the program like this, printf and echo. There we go, x. So that function works perfectly well as well. I'm going to give you a tips, by the way. When you are working with a specific project in a specific directory, in a Linux or Unix environment like I am here, like I am in this challenges folder, it gets quite annoying if you're deeply inside a folder structure and this prompt is taking up most of your screen, like mine is now. One thing you can do, which is a temporary thing and it doesn't save that settings, you can do export home equals $pwd. What this means is it changes your home directory temporarily for this session only, and it sets the current working directory, which means my prompt is now this big and I'm still in the same directory. Alright, so what else do we need? I don't think we need a whole lot more. Right, we need one more function, or what we should call it, and that is the put char. The one function like structure which will put only one character to the screen. And I say function like structure because we don't need to create the function for that. It's basically a one-liner, and that's why I needed that char dupe thingy, because I'm going to create a function macro for put char. So, and if you don't know what a function macro is and how it works, please check out my new video from the day before yesterday about function macros in C. So let's define put char with one argument. And what are we going to do? Well, the only thing we're going to do is we're gonna call the write function, because we're only gonna output one single character, which means if we go to the end here and we check out how our put s function looks, well, we have this check and we call this string length, but since it's only one character we're going to put out, we don't need the string length call. And if we look at the arguments here, this won't change, this is always a 1, and this is just a pointer towards what we're going to print. So this is basically the only thing we're gonna call. So let's define the macro as calling write with a 1 as a file descriptor, and then we make a call to char dupe with the character that we want to print, and we're going to print one single character like this. Quite elegant, huh? No extra overhead from the functions. Okay, so now we have our building blocks. Now we're gonna take on the actual function printf. And if we begin by the signature, so the signature for our printf will be int printf, and we're gonna take in an const char fmt. This is the format string, and then ... because this is a variable length argument function, and that is what I need my own library. If you watched my community post today, I showed you a piece of code, and I asked you all if you could figure out what it does. And that is exactly what we're going to use now. So let's include, I call it x86 args.h, and it's only one single macro. If we open that .h file, x86 args, this is the code that I showed. The only other thing is this if def, so it checks that we don't include this header file twice. So what does this one do? Let me show you by using the code. Sometimes that is easier than explaining. So I'm gonna create an unsigned int pointer. Let's call it p, and then I'm gonna call the macro, which is args, and I'm gonna send this p like this. And let's just try to print this p, but we need to do a typecast. So unsigned char star, and then another star and the P, like this, and return. No, let's do like this. And then we increase P plus equals 4. We move it 4 steps, and then we print it again. And in our main, let's clean this out. We will just call printf with something like %s. %s like this, and then something like arg2 new line. Okay. Print, how do I spell printf? And this uses putz. I think I did it right. Make return. That's not the correct spelling, right? I have a bad keyboard. We're still no value. We didn't make it a void function after all. We made it an int, I think. Yes, we did. So return 0. Okay, compiled without errors, and if we run it, boom! But we do only see one. arg1. Right. I remembered wrong, because we can, as you can see, we can already access the FMT, so we don't need that. This is only for the arguments. So basically, this is my own implementation of what is called va-arg, which is a bunch of C macros basically, or perhaps some of them are functions as well, I'm not sure. But you use these functions to handle those variable length arguments. I have actually never used any of these, but I wanted to try to write my own implementation of it, and mine is a little bit easier. They are a little bit more complex with more arguments to their functions, etc. The only thing I do is I create an int pointer, and I call the args with that int pointer as an argument, and then you just reference that when you want access to the first argument. And if there are more arguments, then you just increase the p variable by 4 every time you want to point to the next argument. And in that way you can have basically an infinite number of arguments to a function. Okay, that's all for right now. I hope you want to subscribe. Okay guys, welcome back everyone. Now that we have our utility functions done, most of them anyway, we might need a couple of more. We will start coding on the actual printf function. So I'm gonna start to make it work for regular strings and string arguments, as well as char arguments. And then we're gonna tackle the numbers bit. Okay, so I'm gonna read one character at a time, and if we see a regular character, then we will just print it directly to the screen. If we see a percent sign, then we will enter another state, and we will wait for the next character and handle that one differently, and then go back to the usual state. So let's begin by defining the actual state. So let's create a definition which we will call, let's call it wait for a char, basically. So I'll set that to 1, and then I will define a wait for, let's call it format string, and I will set that to 2. And I usually do a comment like this, just to show the bits, because this is a bitwise flags definition. We will probably only need to have one flag at a time, but it's always a good idea to define it like 1, 2, 4, 8, 16, etc., in case we would need to combine the flags, which we probably don't. In addition to this, I will create a type definition for a regular unsigned 8-bit char, which I'm going to call state. So we'll keep our state in a regular char. Okay, so let's begin then. We will define our printf. We have started a little bit here. So I have created a pointer which will be pointing towards the variable length arguments, and a regular parameter for the format string. I have initialized my own library for handling variable length parameters, and we have tested it out like this. So let's remove this, and at this point this pointer is pointing towards the first argument. Okay, so let's see. What do we need? We need a couple of variables. I'm gonna create a unsigned char, which is the one we are reading. And what else? We need a state. I will just call that S, And let's create a regular while loop. We also need a pointer towards the format string. Let's call that, I will just do const char f, like this. Okay, so while we still have a value for this f variable, we will, let's see, first we need to check what state we're in, and we need to initialize those things. What happened here? Okay, so first we initialize this, then we will set our state to wait for character. And we will point our f towards the format string, like this. Okay, so we will loop as long as we still have f, and then we will do an if statement. So if s and wait for char, and this single ampersand is a logical bitwise AND operator. So I could just as easily do this in this case, but since we are using flags, I like using this. Okay, so if we're waiting for characters, then we will switch F. And if we are waiting for a format string thingy, then we will have a different switch. But that too will be for the f variable. Something like this. This should be a pretty good structure, and we want to increase this f pointer one time per loop, so to speak. Okay, so if we start with this switch, what cases do we need? Well, we need a case for the percent. So if we find a percent sign, then we want to, in the next round, we want to look for like an S or a D or something of the sort, which means we will transcend to another state. So I will just set S to wait for format string and break to the next iteration of the loop. I will also have a default case. So this is when we have a regular character. And if we do, I will just put that char on the screen. So like this. It doesn't seem that we will need this C variable, so I'll remove that one. Clean up the typos. So if we get a %, we change states and continue. If we don't get a %s, we put that char to the screen. And if we are waiting for a format string, and we get a %sign, so that's if we have a format string that looks like this, then we want to print that %sign to the screen. So we'll just do put char and the F, and we need to go back to the regular state because we're not waiting for the format string character anymore. So we'll set the state to wait for char and we'll break. So what do we do if we don't get what we think we should get? Like if we have a %sign and something like %x which isn't supported, the only thing we should do in that case is change back the state. So I'll set S to wait for char and break. So we don't print anything. Okay, so we should have enough right now, unless I have forgotten anything, in order to make this work for regular strings without any arguments, that is. So let's just return 0 and end it. We can remove this, and we can remove a lot of these. Let's see what it says. Okay, it's compiled without any errors or any warnings. So let's try it out with just a hello world thingy. Would you look at that? Beautiful. But what happened to the new line at the end? It didn't quite catch that, did it? Perhaps we need to do that manually then. So let's just create another case for when we are waiting for char. So case, and I think it's 10. Let's do something like case 10 and case 13, because sometimes we use both of those. So if we get any of those, then I want to check if percent f plus 1, so the next character, if that is equal to 10, or if the next character is equal to 13. So now I'm handling if we get like one of those. Then we don't want to handle both of them like a new line, because in that case we will not be able to, well, we will get a double new line, which is not what we want. So we will check if the next one is also one of these two, and if that is true, we will simply increase f once more, so we just make a jump over it. That should work, right? And we will put char 10 and break. I think this will work. Let's try it out. No, it did not. Why is that? What if we were to do both N and R? Should be the other way around, I think. Like this, a Windows style new line. Okay. Printf hello world rn. Let's compile this one and we run it, and then we try it out with strace. strace is a great tool for analyzing system calls. So we see all their arguments and the result of the system call. And in cases like this, it's quite nice to have something like that. Okay, so let's see what happens. We should see a, let's just do this, 2 and and we grep for write. Write one hello world. It sends the entire string. Now that's pretty weird. But we are telling it to... Maybe it's not calling the right function. What if we were to add a 2 after each function names? So it's not colliding with the regular functions with the same names. So this will be strlen2 and put s2 and printf2. This should also be strlen2 and wait for char. Put char 2 and printf2. What happens now? Did I miss anyone? Implicit declaration line 69. Put char 2. Okay, it's compiled. Hello world. No, hello world. That's interesting. What if we were to do an strace then? And if you wonder what this means, those messages that we see here on the screen, they are sent to the standard error buffer, and the regular program output is sent to the standard output. What this command does, it smashes them both together. So 2 is standard error and 1 is standard output. And this redirects standard error to standard output, which makes it possible to grep for stuff, even in this type of thing. Okay, let's see. Write 1, write 1, write 1, write 1. Okay. Looks nice, but what about the first? Hello. What happened to the age? So f equals fmt while f plus plus. Perhaps we need to set this in parentheses so it not increments it directly from the start. And now I don't think we need this case anymore. Let's see what happens if we comment this out. Okay, the new line cell works, but we have this problem still with the first character. So let's retrace our steps. We set f to fmt while blah blah blah. This should not alter the pointer until the next iteration, I think. Perhaps it does it directly, because we don't have any other thing that can disturb it, right? So case % is not happening. The only thing is default, which does put char on the F. And then we have a little else if statement, which shouldn't happen. Okay, that's probably it. I thought the while didn't increase this pointer until the next iteration, but perhaps we can do something like this instead. Do and at the end we will do while %f plus. Maybe we even need to do ++f in this case. Let's see what happens. Okay, now it works. Great. So, if you wonder what I did, there are two ways of creating a while loop. It's the regular way, like this, which will loop all the code in here, and it will check this condition at the very beginning. So if this is not true, nothing will be evaluated in this while loop. But sometimes you don't want this conditional check to happen on the first iteration. And then you can just put do here instead. And at the end, you put the while and the condition. So this means that these lines will always happen at least once. And then at the end we check, should we continue the loop? And this was a good example of when we needed to do that. Okay, so let's see what happens if we do %. If it works correctly, we should get, let's put some text afterwards as well. We should get 1% sign on the screen and then the ABC afterwards. Yes, great. Okay, so that works. Now we're gonna do a little bit more advanced stuff. We're gonna take care of the arguments. So we have this p pointer, which is currently pointing to the first argument, which means we should, let's see, in the default case, when we have a failed % with a bad sign, we shouldn't print anything to the screen. Sorry, this is wrong. Default here. We shouldn't print anything to the screen. We should transcend into the wait for char state. But we should also increase the pointer, because if we are calling printf, and let's say hi %s, and then something %x, which is not supported, and then something else %s, which is supported. In this case, we will have 3 additional arguments. So let's say we have a string variable called name, and then we have some foo, and we have some bar. If we're not incrementing when we fail to print foo, this will be unsynced, because this % refers to the third, which is this, and everything will be out of order. So this should fix that problem. What else? Well, let's see, default. We would put in, let's begin with string. What shall we do if we encounter a %s? We already have the pointer p pointing towards the correct argument, so we should basically just send that to puts, and we need to do a typecast, so unsigned char star, and then another star, because we are pointing towards a memory space which contains an address to the argument. So we need to go into that address and grab the value, and that's why we need the double asterisks. So something like this, and then we need the actual pointer as well, and then we will just increase this one. Right, we need to increase it by 4, not this like this. So p plus equals 4, because every memory address in my system takes up 4 bytes. Okay, we also need to change state. We need to go back to the wait for char state, and finally we'll break. Okay, let's see if this works. I will just create the pointer like this and point it to something in the data segment. Let's put in my name. And then I will do like this. And I will send P. Okay, let's see if this, oh, what happened here? Put S, we don't have put S. We called it put S2, right? So put S2, And another typo at line 92. You probably caught that error. And it compiles. And it kinda works, no? Hello, hello. So what are we seeing here? It prints out hello, and then it prints out the format string. Okay, so we are probably off by 4 bytes. Where is it? Here. Let's do an increase of this plus equals 4 from the beginning. Right. Yes, let's do it like this. And we make and we run it. Okay. That's not correct either. I just came to think about something. It is an int pointer, so perhaps it jumps 16 steps if I increase it by 4. Is that perhaps the case? What if we were to do just this instead? And wait for char, wait for format, and we come here, and we will just increase it like this. Let's see, we break out here, and we come down here. And we will increase in this case as well. Okay, there we go. So when you increase an int pointer, it jumps 4 bytes because an int is 4 bytes. And when we do what I did, we increase it by 4, then we jump 16 bytes, and we end up totally wrong. Let's see what happens if we create our first example again, when we have a variable pointing towards a string in the data segment. And we will just send the pointer like this. Still works. Beautiful. Okay, so now that we can send string arguments to the printf function, the next step should be rather straightforward. We will do the same with chars. So let's go into our switch statement for the wait for format string section. And let's create a case for the C character. So what shall we do if we get a C character? In this case, we should call our putchar to a function, and we shall send the next function or parameter in line. So this time we should typecast this as an unsigned unsigned char without the star, but still this star, I think. Let's try that out first at least. And then we increase our pointer. We set our state to wait for char, and we break. So let's see if we can send the contents of a char. So let's remove this code, and we will put in a char named C. I will set this to the letter X, and I will just simply change this S to a %C instead, and this I will change to C too. Okay, let's see what happens. It compiles, and it works. Beautiful. So let's see what happens if we use both of these. So we have two arguments. So let's put back our P pointer, and let's point towards my name again, and let's just put something like this, and then we will put our P right here. So something like this. Let's see what happens. And it works. This is fantastic. Let's see what happens if we change place for these two. I want to see that it works properly with the increase, so it's not a problem that the char is 1 byte and the others are 4. So let's change this to a C, and this to a S, and this to a C, and this to a P. So it should say hello X and Jonas ABC if it works. Yes, works perfectly fine. Great. Now we do only have one thing left, and that is to print out a number. And that sounds simple enough, right? Well, maybe not. Because in order to print out a number, we must convert that number to a string. And this would be very easy if we were allowed to use the standard C library, because there are a lot of functions like that. But we're not allowed to use that. So we need to code our own function which transforms an int into a string of number characters. So there, in the standard C library, there is a function which works in the other direction, which is called A2I. So this takes in a string and gives out a number. So let's name our own function I2A instead, and a 2 at the end. Okay? So int I to A2. Let's see. It takes in an int n, and it returns a string. So something like this. So how do we do this? Let's say we have the number 1, 2, 3. If we were to divide this number by 10, what do we get? If we were allowed to use floats, we will get 12.3, right? But we don't have any floats. So this will result in the number 12, and we will get a rest number, a modulus of 3. So if we take this 12 and divide it by 10, okay, this is a bad representation. Let's do something like 12, and then I will put a 3 in parentheses. And if we divide the 12 by 10, we will get 1, and then a carry of 2, right? Because the 2 is what's left after we have taken 1 times 1 times 10. Okay, and then we have the single digit left, and then we just use that. And if we were to do this, I haven't tried this before, but I have thought about it, and it seems it should work, right? Because here is the 1 and the 2 and the 3. So we would get all the numbers in reverse order this way. Okay? So let's start out there. And we have the n. I think I'll do this by unsigned to begin with. So unsigned int, and let's call this x, and then we will have a unsigned int array. So let's call this x's, and for the sake of this, now we can think like this. There is a limit how big an int can be, right? So it's basically 4.3 billion. And how many are this? We have 3, 6, 9, 10. So we will not need more than 10 numbers. So let's set x's to 10. That's the size. And let's see what we can achieve. I will do this manually first. So I will just set the x to, let's use 1, 2, 3. And I think we might need a y as well. So x is 1, 2, 3. Then I will set the y to x divided by 10. This should generate the 12. So y has the 12. Alright. And we need to store the modulus, but we can put it in our buffer. So let's do x's, and we will worry about the reverse stuff later on. By the way, we don't need this as big as an int, because it's only one number, one digit per variable. So a char ought to do it. So I'll set x is 0 equals, and now we do the same thing. So x modulus 10. So the percent sign is the modulus, which also creates a division, but it collects the carry, the rest bits, the rest digits. Okay, so x's contains that. Then we go to the next step, and x, let's set x to y, because y contains the 12. And then we do the same thing again. Y equals x divided by 10. And this time it's 12 divided by 10. So we should get a 1 in the y. And in the x's, we should get the 2, right? If we do x modulus 10. And then we will just do something like if y is less than 10, we will simply do x is 2 equals what we have left, which is y. Something like this. I'm not sure how well this will be working, but we'll see. And I will cheat a little bit and do the printf here. That's only because I need to know if this works or not. But as I mentioned before, during the development I am allowed to use libraries, but the final product can't use any external libraries. Okay, so now we print. What do we print? We should print something of the like, it will be 3% these here, right? And a new line, and then x is 2, x is 1, x is 0. Okay, and I will temporarily include the stdio. And then inside of main we will just call this function, and we called it a to I to a2, and we supply number 1 2 3 like this. Oh, I didn't remove that, right? No. It compiles. And we get 1 2 3. It seems like this is working just fine. Great. So now let's see if we can make this into a loop of some kind, because currently we did do every iteration manually. So how do we figure out where to put the respective numbers? Loop. Let's start there with the loop, I think, because we have this if statement here. If y is less than 10, then we should do something. So we can loop until y is less than 10. Let's do that. So while y is more than 9, then we should have this loop. And the first step is always to put x to something. And y should, from the beginning, be set to n, which is the number that we are supplying as a parameter. Okay, so far so good. And then we will do the actual calculations. So y equals x divided by 10. And how do we know in what position of x's to put it? Let's just put it at the first position for now, and then we will worry about the reverse order later on. Which means that we need a pointer as well. So unsigned int, no. Yes, it should be an int. Unsigned int p, and we will set p to x's. So y equals x, and then we do x's plus plus equals x modulus 10, something like this. And this will loop until y is less than 10, and then we are down here, and then we should do one additional x's equal to y. So x's equals y, like this. Can remove all of this stuff right here. Let's print out these just like we did before to see if it works the way we intended to. Okay, an error, x is plus plus, p equals x's, incompatible pointer type. Oh, not x's, we are using the wrong variable. Right. I think we should use x's instead, by the way. So let's remove this one. And let's create a pointer out of x's instead and remove this pointer. And then we will set x's equals Malloc 10. And we shall remember to free that one. So x is equal Malloc 10, x's. But now we have changed the x's. Maybe we do need that pointer after all. Let's just do it like this. So x is equals Malloc, p equals x's, and then we will replace those with p. Something like this. Okay. Oh, that's quite a lot of errors. What did we do wrong? Okay, we don't have Malloc. We will include Mallocs. Include stdlib.h. Okay, and now it compiles. Okay, we did get the one to, okay, we freed the wrong variable. Right, yes, we need to free p, not x's. Okay, 1, 2, 3. It works in our easy example, but it won't work for anything just quite yet. It will fill up all of these places. So what do we need to do now? We need to plow through this buffer in reverse order, and we need to interpret the numbers that we do have there, because what we have at each position is like 5 or 2, etc. But 5 or 2, etc. has different meaning for a char, because char is using the ASCII table. So let's present it like this. So if we have, for instance, a %C and then 61, then we get a 6. No, doing it wrong. %C, I think we should do it like this instead. So 41 in hex, that is a big A in the ASCII representation, and it's B, etc. So what we have is 0, 1, 2, and we need to change that to the ASCII representation of the numbers. So can I somehow get it from this printf version? What do we need? We need a %C. And what do we get if we just do a 1? We get the 1. 3. 0. Do we have hex stamp installed here? Yes. Okay, let's do hex stamp instead. So let's printf the number 1, for example, and then we do a hex stamp. Here we can see it's 31. And if we were to do 5, it's 35 in hex. So that means we have a span from 0, which is 30, all the way to 9, which is 39. So basically that means that we want to take a 39 of hex and turn that into a, no, the other way around. We want to take the 9 in hex and turn that into the 39. So we should just be able to add the hex value 30 to any of our numbers, right? Which would mean if we were to do like in 32 here, we should get a 2. Yes, we do. Okay, that makes stuff easier. So now we just have to reverse this and alter the numbers. So let's create macro for the swap. So define swap char of x, and that should be x plus the hex value of 30, like this. Maybe we should add some parentheses too. Okay, so now we have a swap char. Now we need a reverse. Maybe we should have some kind of ending character. Or do we need that? Because axis is pointing towards the last one. So if we start by axis and count down to P, we should be all right. So while axis is not equal, or maybe we should do while axis is less than P. And we need an additional buffer that we can return. Let's make that static char. So static char return, and we'll make 10 of these. Like this. And we need a counter for them as well. X and Y is not needed anymore, so we can take them. Maybe we shouldn't use a while loop then. We will do 4, and we will set x equal to 0. We will loop as long as axis is less than P, and in each iteration we will just increase the x. And what are we going to do? We're going to set the ret of x equal to swap char of x's. I think that should be right. And then just at the end of the loop we will ret x. This has increased. We will set ret plus x equal to 0. Something like that. And we will free that buffer, and we will return ret. Something like that. Okay, so I to A, we need a printf here. Let's do like this. So we will cheat with the printf, and we want to output I to A2 of the number 54321. Let's see what happens. It compiles. Okay, we're on the right track. But it seems like the calculation didn't work out quite right. But let me try something. If we go back here and we do, let's do something like 1 to 1. Five to 2 plus 7. Ah, wait, I have %d here. This returns a string. Let's try it now. So now it should say 1 to 1. Nothing. Who said coding was easy? Okay, let's try another number first. Let's do 5, 4, 3, 2, 1. Nothing. If we were to do an S-trace, we would probably not see much. Three. And an L-trace. L-trace is the same as S-trace, but we see the library functions instead of the system calls. But I doubt that'll help us much because we're not really using any external libraries. But perhaps we see something here. So L-trace. There we go. Okay, so let's check out the L-trace output. That's not much. We allocate the buffer, we free the buffer, we send the printf. So what went wrong? Let's go through the code again. So what do we know? We know that this part works. So we do get the numbers in reverse order into our array. Then what? We do a for loop. X is 0, x is less than p. Perhaps this should be in the other direction, less. I always forget how the memory is, or the memory addresses are growing. X is more than p. Wait a minute. Let's see. X's, p and x's are the same here. Then we increase x's, so x's should be bigger than p. Okay. Hopefully this is it. Segmentation fault. Okay. So let's do the L-trace. Malloc and then crash. And then S-trace. So this is basically negative part of doing everything ourselves with not using any libraries. It gets a little bit tougher to troubleshoot. But let's see, why does this not work? As long as x, do we decrease x's somewhere? No. Okay. Because we definitely should. So each iteration will do x's minus minus. Like this. Okay, let's try it again. 5, 4, 3, 2, 1. Okay, we're getting close. We didn't get the 1, but I think we forgot about that actually. Because we do, so we loop until y is not longer bigger than 9. And then at the end, we put x is equals y. So that should be the 1. But, and x's should still be pointing towards that 1. So when we go into the loop, ret x equals swap char x's should be the 1. Or maybe we don't do the last iteration here. So y-axis is more than p. What if we were to do just another one of those? We'll let ret x equals swap char x's. Let's just try this. And there we go. 5, 4, 3, 2, 1. We have successfully created our own I2A function, which should make the last part of our printf quite straightforward, right? So let's go back to the printf. And let's go back to the wait for format string state. And we'll create a case for the D character. And what should we do when we encounter a D character? We should put string 2. And what should we send? We should send I to A2 of unsigned char star p. And we have that parentheses and that and that like this. We should increase p, set the state to wait for char, and we shall break. Something like that. Okay, so let's clean up our code. Let's remove this printf. Let's go to the beginning and remove standard IO. And let's test if this works. Let's create an int to call x. We set it to 501. No, 5010 is good. And then we will do printf. No, not printf. Printf2, our function. And we will say something like the magic number is %d. Congrats. Something like that. And then we will just give x as the argument. And x is a value. It's not a pointer. You need to take that into account. So we should strip one of the stars, right? Sure, like so. Unsigned char. Because we're going to send a number to that function, and we shouldn't even do char, we should do int, right? Let's try this out. Oh, that's quite a lot of errors. Warning implicit declaration of I2A2. I2A2. What did we call it then? I2A2. Wait a minute, perhaps it's just the order of our functions that messes this up. Could it be so easy? Let's create some function definitions then. So what do we have? We have the char dup2, which takes a const char. Then we have strlen2. Okay, what happens now? Okay, we removed almost every error message. So conflicting types for printf. Const char fmt, const char dot int. Okay, int and void. Forgot to change that. Okay, now it compiled. Let's see if it works. Okay, the number is not the right one, but that's probably because we messed around so much with the typecast. Because let's see where we have the %d. It's right here. It should, I think we should at least have let's see, unsigned char. I think we should at least have one of these stars. $50.10. Congrats! So we have succeeded in creating our own Printf implementation, including an own VARG implementation for dealing with the variable length arguments, and a lot of different utility functions, so we didn't even need to use the standard C library. If you like this video, you should subscribe, because I will create some more C videos soon. And as always, I release an episode every week, and I lift up an older episode as well for you to take a look at. So that's all for today. Thanks for watching, and thanks for today. Okay, sup guys. I need to add a little thing about my Printf video. So, one of my subscribers, one of you guys, mentioned that the Malloc is not a system call, it's a library call. It's included in the standard library, which means that I shouldn't have used it in my challenge with Printf. So today I'm going to try to come up with a different solution with regards to Malloc. So first I need to tell you a little bit about how Malloc works. So if we take a look at the memory of a process, this is the entire virtual memory space that gets allocated when you start a process, like a program. At the bottom here in brown, we have the data segment and the BSS segment with initialized and uninitialized data, such as constants and things like static variables and stuff like that. We also have a text segment, and that is our code. So then we have the heap, and the heap is the dynamic memory which we can control with a library calls such as Malloc. And at the top here we have the stack, and the stack is growing downwards, and the heap is growing upwards, and in between here we have blank space. We have uninitialized memory, which both the stack and the heap uses. Okay, so every time you do an allocation, so let's say you use Malloc to allocate 1500 bytes, and then you'd make another allocation, and maybe a bigger allocation, and then a smaller again. And Malloc needs to keep track of all these different allocations. And so the heap is growing upwards when we do these allocations. And one special structure, the break. So the break is the demarcation line between the top of the heap and the uninitialized data segment. So this is moving upwards when we do these allocations. But then we will give one of these back. So we free this allocation, and then the break will be moved downwards.
And if we free this allocation, okay, whatever. So if we free this allocation, then the break will move down again. And if we allocate more memory, then it would be moving up again. But what if we give back, if we free this one? Then the break will not move, because it only moves when you give back something located on the top of the heap. So the next time you will do a memory allocation, Malloc will check if any of these holes fit. So perhaps you're asking for more memory than any of these holes can accommodate. Then you will allocate it on the top of the heap and the break will move. But if you make a smaller allocation, then it will fill this hole instead, and the break won't move. So basically we can conclude that Malloc is aware of these data structures that corresponds to these memory allocations, and it's a quite advanced function to keep track of all this stuff. But the kernel only has to be aware of the top of the heap. So the actual syscall is called sbreak. It's spelled like this, SBRK. And you give one argument, and that is how much you want it to either move upwards, the break, if it's a positive number, and the negative number will move it down again. And if you give it a 0, then you will just it will be returning the current memory address of the break line. So this makes it possible for us, I think, I haven't tried it yet, but to create a function macro, which we could call like let's call it Malloc. Let's call it Malloc2, and it takes the same argument as the regular Malloc. So if we want 10 bytes of data, we do like this. And what will happen then is that this macro will just call sbreak and move the break 10 bytes upwards and return the memory address of the old break, which is the start of the allocation. So basically it behaves just like the library called Malloc in this case. The problem is if we want to free a specific hole, so to say, that won't really work because we're not aware of all the allocations. But we could make it like this, as long as we don't mix the real Malloc with our macro version. We could create another macro which we could call free all, which basically just does sbreak and minus x, where x is the total amount of memory which we have allocated using this macro. So that is the solution I want to try out. So we have two options. We can allocate memory and it will save it to a global state, how much we have allocated in total. And
then we just free all of it at the same time. Okay guys, let's see if we can turn this into code. I will just log into my server real quick and attach my screen, and I'll create a new file. Let's call it malloc2.h. And we need a global variable which knows about the memory allocation. So it'll be an unsigned, let's make it an int. Perhaps in a later version we'll make it a bigger structure, but this will work for now. And let's just call it something like alloc, like this. And then we need two functions, or rather function macros. So let's begin with our malloc function. I will define this as malloc2, and we'll give an x, and the only thing we'll do is moving the s break like this. And then we will increase the allocation by x as well. That's all. And when we free this memory all at once with our free all function, and this will not take in an argument, and what this will do is it will move the s break to minus alloc, and it will 0 alloc. And this should be all, I think. I need to check where to find that system call, by the way. S break. It's in the uni.std.h. So let's put the include here as well. Like so. And let's test it with our printf. And if you haven't seen my printf video, please check out the creating your own printf that I released, I don't know, a couple of days ago. So instead of uni.std, we will include our local malloc2.h, like this. And then I will search for malloc and change this to malloc2, like so. And I will search for free, and here we free the p. Let's see, free p. I think I will remove this. No, I think it'll work if we do free all here actually. And we'll go to any next occurrences, Okay, there are none. Great. Let's see what happens. Make clean, and we will make printf. It compiles, and we will just run it. The magic's number is 5010. Congrats. Okay, so we have successfully created an own very simple and naive implementation of Malloc, but it works fine without any external libraries at all. And we've included it in the printf, which is now completely free of any external libraries. And sorry for the sound quality in this episode. This is a bonus episode, and I needed to use another computer with a worse microphone. But I hope you learned something from this anyway. Thanks for watching, and thanks for today.
Okay, welcome everybody, and welcome to today's class. Today we're gonna code our very own TCP server. We're gonna listen for a TCP port, and when we get a connection, we will send a predefined message, and we will close down the program. So, very simple server to demonstrate how it's done. And then we're gonna build on that code later on. Okay, so last time we coded a file called sockets.c. This one. This did the opposite of what we're gonna do today. This is a TCP client that connects to, in this case, www.yahoo.com on port 80. So that it's the HTTP port. It connects and sends the head command, which checks the headers of the server. And then it just prints them out on the screen. So what we're going to do today is quite similar, only the opposite. We're going to be listening for a port instead. And then we are going to connect to that and see what happens. Okay, so in order to make an outgoing connection, we first initialize the socket, then we fill the structure with the IP address, port, and address family. We use the connect in order to connect to the server, and then write and read to read and write to the server, and then we close down the connection. We're going to do quite similar things today. We will initialize our socket the same way, and we will use the same structure for the server. But instead of the inet address function, we're just going to use a 0. That means we're listening for all the IP addresses on all the IP addresses on the server. We're going to use the same way of defining the port and the AF family. But instead of connect, we're going to use a very similar function, taking the same arguments, producing the same result, but it's called bind instead. And that basically binds this socket or this structure with this initialized socket. Then we're going to use the listen function to establish the listening on a TCP port. And finally we're going to use the accept function, which basically waits for an incoming connection and creates a new socket for that one. Okay, I'm gonna copy the include files from our old project to speed things up a little bit, and then I will create a file called serve.c. So we'll begin with our header and all the age files, and we'll do everything inside of main just to try this out. Last time we used one socket file descriptor. Today we're going to use one for the server and one for the client. We also need a socklen t variable, which is basically an unassigned integer, and we'll call this one address length. This is necessary for the accept function. And then we're going to create two sock address in structures, one for the server and one for the client. And I'll start by erasing these structures using the memset with a 0. We could use the b0 function, but it basically does the same, so it doesn't matter which you choose. So we'll erase the serve and the client, and probably this is not necessary, but it doesn't hurt anything, and sometimes it's good. Alright, so now it's clean. We will initialize our server socket the same way as we did before. So the AF inet family and the sock stream domain and a 0 for the third argument. And if socket is less than 0, we will print an error message telling us that socket failed, and we'll return -1. Okay, so now we have our socket initialized. Now we're gonna fill our serve structure, and we begin with our syn family, which is AF inet for internet, and we'll use serve syn address s address, and we'll just set a 0 there for all IP addresses. We could also use in address any, which is a constant that does the same. Okay, and then we'll set the port. Let's create a couple of constant definitions, or at least one for the port, and I'm going to use 8181. And the syn port will be sent to the HTON S to produce the right kind of ending a number for the port. Okay, so that's the server structure. Now we're gonna bind it together with the socket. So we'll call bind, and we'll send the socket as well as the serve structure, and we need to typecast this the same way we did struct sock address, the same way we did with the connect function last time, and we'll send the size of serve. Okay, so bind works that way that it returns 0 if it works. So if it's not 0, we will print an error message telling us that bind failed. And then we will return -1. Okay, so that's socket and bind. The next step is listen. And listen takes two arguments. One is the socket S, and one is the queue. So the queue is basically how many queued network connections are we going to keep before dropping them. So if we set a 5 here, for example, then we can have 5 simultaneous connections. And for the sake of argument, let's put 5 in there. And I think listen works the same way, that if it... let's double check the return value. So, yes, it's a 0 if it works. So we can do the same way that we did with the bind. And we'll print out that bind failed. No, listen. Listen failed. And we'll return -1. So socket, then bind, then listen. Now we are listening to the port, and it'll show up in netstat, for example, that we're listening on 0000:8181. And now we'll just accept the connection. And accept takes 3 arguments. The first is the server socket. The second is the server structure. Same syntax as the bind directive. And the third is the address to an int. That's basically my address line. Let me just set this to 0 from the start. It doesn't really matter. So we'll send the address to that one. And why do we do that? Well, that's because accept will write the length of the address, how many bytes the address is, to this int variable. So we'll just put it right here, like so. Don't think we need to typecast anything. We'll see what it says. And we need to take care of the return value, because the return value of accept is a new socket file descriptor connecting the client. So if we pass the C to read, we will be reading from the client. And we will check if C is less than 0, then accept failed. And we'll return -1. We will also close the socket. It doesn't really matter, but it's good to code it like that. If you open something, don't matter if it's a socket file descriptor or a regular file descriptor. Remember to always close it if you don't need it. Same with dynamic memory allocations. Always free the memory allocations. So we'll do the same here. We'll close S and return -1. Okay, so if it didn't return a value less than 0, it means that it works. So let's print something. Client connected. We can also do a similar thing for or after the listen function. So listening on $0,000:%d, and we pass in the port. Let's use a constant over here as well, like so. And what are we going to do when the client has connected? We're going to send some predefined data. I will create a buffer. We're not going to read any real information here, but we need to take care of the input somehow. And we'll create a char pointer with statically defined data. Okay, so let's begin by reading from the client. So we'll just do read and see buff 511. Then we will prepare our data, and let's pretend this is a web server. I will not follow the protocol at this point, but I'll just return something like HTTP version 1.0, something like that. And we'll write to see the data with the string length of the data. Then we'll close the client connection and the server connection and return 0. And that should be it. Let's go look through our code. So we begin by zeroing the variables. We initialize the server socket. We prepare our structure. And then we will use a bind to bind the structure together with the socket file descriptor. After that, we pass on the listening function in order to start listening for our port. Then we'll do the accept. At this point, the accept function will be waiting. It can wait an hour if so. It will be waiting for a connection to connect, or a client to connect. And as soon as it connects, the accept function returns a new socket file descriptor for the client. Then we'll just use that client file descriptor to read and to write and to close. And that should be it. Let's save this one and see if we invented any bugs. No, it compiled right from the start. Okay, so let's start up the server like this. No error message. Let's do a netstat -an grep listen. And as we can see, we are listening for port 8181. And then I will just do a telnet connection to localhost. And I use this env stuff in order to clean the environment variables, because telnet has a tendency to send these environment variables through the connection. And I don't want any additional data sent to the server. So 8181, and we will send something like head, pretending to be a web client. And as you can see, we did get the HTTPD version 1.0 back. So our program works. What have we learned today? We have learned to create a TCP server. by creating a socket file descriptor from the socket function, preparing the structure, binding them together, listening for the port, and using the accept function to accept the client. And then just use the regular read and write functions, or system calls rather, to send and receive data, and then we close the connection. We will be adding on to this client server, and we will be creating our own sample web server step by step. And this was the first step in order to try out how to create a TCP server in Linux C. Thanks for watching, and thanks for today.
Welcome back everyone, and welcome to today's class. Today we are gonna create our own HTTP server, and we are gonna make it quite modular in different functions, and it will use the fork function in order to be able to receive several connections at the same time. We will also create the new route method of serving web pages. So we will disconnect the connection between the URL and the file part of it. So this part. Before, this was always connected to a real file or a real directory on that server. But nowadays, especially with the new cloud platforms, we use something called route instead. So we predefine different strings. That's this part of the URL. And then we handle them with a different function, or at least a different part of the code, rather than serving a specific file. And if we need to serve a specific file, we usually do that dynamically instead. Okay, I will create a directory for this server, and I will just call it httpd. The D at the end means daemon, and a daemon is another name for a server software. So it's quite common that different types of services like FTPD and HTTPD and SMTPD, that different types of services ends in a D in the software. Okay, so let's begin by creating a file. I will just check my Vim config real quick. If I remember where I put it. Here it is. I will just copy this command so that my tab works the way I want them to. And we'll create a file called httpd.c. And I will just do a simple header, and I want to, let's do this. I will do head-15 and steal the includes from our last server project. Oops, I didn't want them inside of my comment. There we are. Okay, so the includes are done. I will also define a I will define a static
I will define a static listening address of 0000. So we're basically listening on all interfaces. When you create this code, I recommend that you bind it to localhost. If you don't have a firewall, that might be helping you out, because if you tie it to this IP address, everyone on the internet will be able to access it. And perhaps that's what you want, but you should at least be aware of that. Okay, so we'll begin in our main, and this will be very slim. I usually try to make my code that way, so that the main function is as tiny as possible and everything is done by functions. However, we need a socket file descriptor, but I won't initialize the socket directly here. I will just do a call to a init function. Let's call it server init, like this. And we won't give it any argument at all. Okay, let's begin there. So we'll create that function. I will make it an int, because the socket file descriptor that will be returning is an int. And in here we will do as much as possible. We can do this, by the way. Let's put the port number in there. So I will still... No, let's do it like this. Sorry for changing a bit to and fro, but I want this to be perfect. So let's make the int function able to receive arguments like this, and we will create a char for the port number. Then we'll check if arguments is less than 2, and if so, should be if here, nothing else. And if arguments are less than 2, that means that we're just starting the program like this with no arguments. So we will give an error message saying usage %s and the listening port, something like this. And the argument will be argv0, which is the name of the executable. And then we'll return -1. And else we'll just set the port to argv1, like this. Now we can send the port as a string to the no, not as a string. We will use the a to I in order to convert it to an int, and then we can use it in our function. So in here we will just have like a port number like this, and we will have an S here as well, which will be the return value. And we'll initialize the socket, so af inet sock stream and a 0. And if s is less than 1, I believe, let's double check that part. I never seem to remember the return values. On error, -1 is returned. Okay, so let's do like this. And then we will just return our own 0. It's always a good procedure to put a comment on top of your function describing how the return value works. So returns 0 on error, else or it returns a socket FD. Okay, so socket is done. We'll also need a struct sock address in for the server, like this. We don't need the client in this function, I believe. We'll see. Okay, so the socket is done. Now we're going to do the bind. After we prepare our socket struct. So sin family is AF inet serve. I'm not describing every part of the server sock address in structure, because if you want details about that, you can watch the video about the sample TCP server. I will just discuss it briefly, and I will go deep on all new things in this video instead. So sin address source address, no, there should be a dot there. Sin address source address equals inet address, and then our constant listen address, like this, and serve sin port equals 8 on S and the port number. Okay, now we will bind the socket file descriptor together with the structure. Sock address, and we will put in the serve and size of serve, like this. And let's check the return value of bind as well. On success 0, on error -1. Okay. So if this has a positive value, like this, then we want to close the socket, and we want to return 0. Maybe we should have a global variable for the error messages. We could do that. We'll just call it error. I'm not sure if that's available, but we'll see. Okay, so here we will set the error to socket error. And in this case, we will set the error to bind error. Then we can use that in our main function or other functions to just print out what went wrong. Okay, because this is a global variable and it's pointing to this, and this is a constant static text which is saved in a special part of the memory. It's called the BSS, and that is available from all functions. So the error variable is a global variable, so it's available everywhere, and that is this message as well. Just a little informational parentheses. Okay, so when we have bound them together, we will listen for the connections. So we'll just give the S and the number of simultaneously or awaiting connections. And let's do 5. And let's check the return value of listen. 0 on success, -1 on error. Okay. So if this returns a truthy value, we will close the sock, we will set the error to listen error, and we'll return a 0. So this was socket, bind, and listen. Now we'll just return our S. This structure is local to this function, but I don't think we're going to need it anymore, so that should be okay. Okay, so now we have initialized the, let me just do a couple of these temporarily so I don't have to write at the bottom of the screen. Okay, so now we have initialized the S, and let's see if it's false. Then we want to print to standard error the message contained in the error variable, and we want to return -1 and exit the program. And if not, then we are up and running. The only thing we have left before we can accept the connection is the accept function. But I will handle that in a loop. So we'll do a never-ending while loop. And we want to, let's see, we want to get a socket file descriptor for this part as well. So C equals serve, no, client accept. And we will just send our S. That ought to be enough. Like this. So we'll loop through this one, and we will there. Maybe we should add a couple of messages as well. So something like this. listening on %s and %c. And that'll be listen address and our port. And then we'll loop through this one, because this is a blocking call. It's gonna wait for a connection and then hand it over to us. And when we get a connection, then we want to check if it's negative, if it fails somehow, and if so, we want to print out an error message, std error, and the message. But we're not gonna quit. We will just go to the next round of the loop. So continue like this. And if it does work, however, then we will print out a message, incoming connection. Maybe we can add more to it later on. But for now that's okay. So incoming connection, and then we want to fork. We talked a little bit about fork the other lesson a couple of days ago, and fork creates a copy of your program, so it runs in 2 instances from here on and forward. And we get a return value from fork, which is one of the following. For the main process, return the new process's ID. For the new process, return 0. So that's how fork works, which means what we want to do is, if we are the main process, we will just move on to the next round, to the next cycle in the loop, and do the next client accept. But if we are the new process, then we want to handle the connection. So if fork is 0, which means this code is for the new process, then we want to do client handle connection. No, not handle. Everything handles something. Client connection. Let's do it like this. And the only thing we need to say to that is the server's ID and the client's ID, the socket file descriptor. That ought to be enough, and we don't need a return value or anything. And else we'll just continue, but we don't need to specify that. Okay, I think this should be enough. It will never come to this point, so it will return error if it does. Okay, so now we will. So in the next step, we want to do the client accept function. And we'll put this on top of this. So let's do the return value like we did before. So returns 0 on error, or returns the new client's socket file descriptor. Easy enough. And what did we call this? We called it client, I don't remember. Client accept, okay. Client accept. And we will have the socket file descriptor as a argument, as the only argument, yes. Okay, what do we need here then? We need a client file descriptor, and we need an int for the size. It's a soclen t, I believe. Address size. No, it should be called address length. That's more specific. Okay, and we also need a struct sock address in for the client, like this. And I want to memset that structure with zeros, size of client. Okay, so what do we do? What do we need to do here then? We need to run the accept function. And accept takes 3 arguments. The first is the server's socket file descriptor. The second is the structure. So this part is 0 at the moment, but after accept has succeeded, this one will be filled with the client's port and IP address and so forth. And that is also why we need to specify this third argument, which is the address of this address length variable. So I will just set that to 0, and then this will contain the size of this. Right, so we do the accept, and we will put the return value inside of our client socket file descriptor, like this. And I believe it returns -1 if it fails, but let's check that. So accept, and we have on success returns the file descriptor, on error -1. So if C is less than 0, then we'll do just like we did before. We will set the error to accept error. And maybe we should, no, let's do it like this, and we'll return 0. And if not, we will just return C. That ought to be enough, I think. So to recap a little bit, we read the listening port from the command line, put it in the port, we execute our serve init function with a port as an argument. And this one will just do the socket initialization, fill the server struct socket address, and then we'll bind them together. That is the socket file descriptor and the structure. We'll do the listen as well. And if any of those returns with a failure, we will set the error pointer towards different error messages and return 0. And if everything goes fine, we will return S, our socket file descriptor. And then we will initialize the loop where we will loop client accept. That's also a function. And this one will just accept the connection using the accept function and return the new client file descriptor. And if it returns 0, it prints the error. If not, and continues to the next cycle of the loop. And if it works, then it will fork, and the new instance of the program will run client connect, sending both file descriptors. And the main program will just go to the next run of the loop. Okay, that's quite a lot of quite advanced code. So we'll see if it compiles. We probably have to tweak it a little bit. This client con function isn't done yet, but I will just put in a dummy function for now. So void client connection int s int c return like this. Let's see what happens. Okay, we got an error. Sock address undeclared. Sock address undeclared. It should be struct sock address. I did the same mistake several times when we did the other server video as well. I seem to be very used to using typecast for every struct, but they don't. So let's see. Sock address will include the struct sock address. And what about the client? This time I remembered correctly. Alright, let's compile again, and now it works. Awesome. So let's see what it does. It says that we should supply a listening port. Alright, let's do that. Let's do 8282. Okay. That shouldn't be a V there. Let's see why that happened. Should be a D there instead. Alright, let's do it again. Okay, I'm not sure that's better. Very long port number that is. Okay, so port equals argv1. What is okay, port is a char. We convert it into a int here, but we don't save that, so let's just do %s here. Okay, this time it listens to 8282. Let's just do a netstat so we can see that it is true. Yes, here it is. Good. We won't be able to send or receive any data because we haven't done these functions yet, but we should at least be able to connect to it. And let's see what happens. 8282. Okay, we're connected. Incoming connection. We can do a PS and see if it forked. Here is one instance, here is one instance. And we can also see that this has one process ID and this has another. So everything is behaving the way we want it to. And I think that would be good enough for today. Because I'm going to do a series with this HTTP server. So today we made the base of the application, and next time we are gonna do something more. We're gonna handle the client connection, take care of different HTTP headers and commands, and we're gonna take care of the routes and serving web pages. Thanks for watching, and thanks for today.
Okay guys, welcome to today's show. Before we start, I just want to mention that on this Friday, the 21st, I will have a live stream where we will create our very own in-memory cache database, like Redis, but faster. That is the intention anyway. And in anticipation of that live stream where we create a database, I will today create a data structure, a form of a binary tree, my own way of implementing it, which will be able to store data effectively. So that's what we're going to do today. And if you want to have more details about how the binary tree is constructed or designed, I recommend watching my last episode where I draw the tree graphically. But today it's all code, so let's begin by creating a directory for this project. Let's just call it tree, like so, and I'm gonna set the home directory to my current working directory, so it makes stuff a little bit easier. And as usual, I'm gonna use Sociopath SCP client in order to alter the files live on my Linux server. If you do this project at home and don't have an external server, that's no problem. Then you just do this locally as usual. So let's see, where did I put it? Inside the temporary directory and tree. So I right click and open in editor, and currently this is just an empty directory. Let me just position this a little bit. .c, something like this. And I'm going to create the files. So we need a tree.h in order to keep all our definitions and stuff. And we need tree.c where we put the entire programming implementation. And I will also create a make file to make stuff a little bit easier to compile and recompile. And I'm going to use this same kind of make file as I usually do. So what do we have? We want to compile tree.o, and we need tree.c for that. So we will run cc with possibly a couple of flags. And I'll make this a little bit smaller. I hope you don't have problem seeing this. And we're gonna do -c and the name of the input file, which this represents. Okay, and when we have tree.o, we can compile tree, which requires tree.o. And in order to do that, we run cc with our flags, and then we will do, let's see, we will take the target, and as output file we will have, we will take the source, and as output file we will have the target. So that's a symbol for the target, and possibly we will have some kind of LD flags for the linking process. Like so. I will also create a clean, which will simply remove all the O files and the tree binary. And finally we will do all tree. Okay, so that's most of the make file done. And I will just create those variables. So we have flags and we have LD flags. I will leave LD flags empty for now, but I want to compile this using WAll, and let's do O2 for optimization. And let's also define the standard to be C23 or C2X, because this release of GCC was released right before the C23 standard was released. So that's why they called it C2X, because they were not 100% sure if the feature list would have matched the C23 standard. So that's why. Alright, let's save our make file. Let's save our tree.c, and let's save our h file. And hopefully they have been uploaded. They have not. No, I was disconnected from the server. Let's reconnect. That's a good thing with Sociopath, by the way. Even if you have a lot of files open, if you get disconnected and just reconnect, then you should be able to just save again. And let's see, we save this, we save this, and we save this. There they are. So let's do make. Okay. I need to do double of this, I think. std, oh no, it should be std equals. There we go. So the only error now is that the file is empty. So let's remedy that. I will simply create an empty main, and let's do hello world like so. We return 0, and we include std, no, not here. Let's include our own tree.h instead. We save this one, and inside of tree.h we put all these regular header includes. Okay, and if we just do make, we have ourselves a binary. Hello world. Okay, so that's structuring our project. I will add a couple of more includes. I have 4, which I almost always use in every project. I'm not 100% sure I'm gonna need all of these, but let's prune them off at the end instead, so we don't have to go back here just to include stuff. And let's also include some error thingies. So I want assert, and I also want R number. And in order for them to work properly, I do also need to define GNU source, like so. Okay, so that's a little bit structuring. Now to our real project. So I want to create this kind of binary tree that I showed in the last episode. So basically we will have a, let's see, a couple of nodes. So first we have the slash, for example. In the next level we have another folder such as users perhaps, and then we might have users slash login or something like that, and this grows like nodes in a tree. So we can have basically how many of these as we want. The only limiting factor will be the variable that we store this string inside. When I experimented a little bit on my own, I created a system that only saves this part, so not the slashes. And in this level we only save users, and in this level we save users and login. But I don't think I'm gonna do it that way this time, because what I want to create is a very fast structure based on CPU speed. I don't care if we waste a little memory, as long as it's not extremely inefficient. So if we keep copies of the whole string on each level, it might add a couple of kilobytes at most, and it will make our parsing a lot of easier. So I'll do that, and each of these folders, or nodes as I call them, can contain one or more values. So we might have, for instance, let's say we have users Jonas, we have users Jim, and so on. And those are the leaves. So this will contain a value, for example, and Jim will contain a value. And these needs to be unique in the folder, but we can have a Jonas inside of login as well, if we like. So this creates linked lists from these nodes. So basically it's a couple of linked lists, one per folder, each including the value. And then we have the binary tree consisting of this folder structure. Okay, that's a lot of information at once. So how do we begin? It's a rather, it's a rather ambitious project, creating this binary tree and make it efficient. So where do we start in a project like that? I like to start with the types. So I will have a type which is called node and one that is leaf. And those two together, they form a tree. So a tree can be one of two things. It can be either a node or a leaf. And these are structures containing values in the case of leaf and just links to other levels in the case of the node. Alright, so let's start there. I'm going to create a structure which I will call S node. S is how I name my structures. And what do we need for a node? Well, if we think about the links, there is an uplink to the layer above us. And that is always a node, because only nodes can connect to other structures of the tree. So this is an struct S node, and it goes upwards. And if we are at the top, at the root, then this up will point to itself. It will point to this node. Otherwise, it will point to the node on the layer above. What else do we have? We might have a link to the left, downwards to the left. Let's call this left. Or perhaps we shouldn't use left and right and up, but perhaps we should use the cardinal directions instead. That looks a little bit more precise. So let's call this north and this west. It's west, right? West. Yeah. And we will also have a link to the right, but that's not a node, that's a leaf, because to the right or to the east, we're gonna link to the first leaf in that arm that goes to the right. Okay, so there we have our links. We do also need to save our path, and I could make this a char, but I don't like that. I want to create my own, a little bit more precise types or integers. Let's do a type def, and I want to have a 32-bit int. So that is, in my case, an unsigned int, and I'll call that int32. I will also have a 16-bit int, and that is an unsigned short int, and I will call it int16. And finally I want the 8-bit int, and that is simply an unsigned char. So int 8, and the int 8 is the one that I'm going to use here, right here. So int 8, and let's call it path, and let's do it like this, as an array of 256 bytes. So this will contain the whole path, not just the current level. And what else? We're not going to have any level, we're not going to have any values. So that's nothing to think about. Perhaps we should do this as an U-tree instead, because we don't know if... I think I will make the root a little bit different, so it's a node but it's not a node, and perhaps we need to do this. Let's have it like this for the time being, and we'll give it more thought when we need to. Okay, and we need to give this a name. So typedef struct snode, and I want to call it node with a capital N, like so. Okay, so the most of the node is done. Now we need to create our leaf. So struct s leaf, and what will a leaf contain? If we begin with the connections, it will have a northern connection, right? Or rather, it will have a western connection to the leaf on the left, or to the node if it's the first one. So I think I will go back here to, let's do an S node here, but here we will do a tree instead. So struct, no, not struct, it's a union, and I'm going to talk a little bit more about unions later on. So union U tree, and this will go to the west, and perhaps we will have a link to the right as well if there are more values. So it will be a struct s leaf, and it goes to the east. Okay, that's the two links. We will also have a path. So, and I don't think I'm gonna call this a path. No, let's call this a key, because it will be like a key in a regular object type data structure, which this kind of is. And let's say a key is 128 bytes, and we will also have a value, but the value I will not store inside of here. I will just do a pointer to the value, so we will allocate that separately and just point to that value, because the key can be rather small, right? But the value can be rather large. Perhaps we have a big JSON structure here inside of this or something, and it can also be a lot less than 128. So by doing it this way, we can add, let's say, a 16-bit count, or perhaps size, and that is the size of this value. Okay, so yeah, that's basically it, and we will give this a name as well. So type def struct s leaf, and leaf with a capital L, like so. And finally we will create a tree structure, and that's a union. So it'll be union U tree. And what will the union contain? Well, it can contain one of two things. Either it's a node N, or it's a leaf L. And that's the thing about unions. All the different variables in the unions share the same memory space, which means I can only have one node or one leaf, not both at the same time. But in a structure, we can have everything at the same time. So let's give this a name as well. So type def union U tree, and we will call it tree like this. Okay, so let's create one of those structures. I'm going to create functions that do that, but the root of the tree I'm going to initialize using the new tools for that in the latest C release. So I can do something like tree root equals, and these curly brackets, and I need to have the definition of the node. By the way, I forgot something. I do also want to have a tag. So tag, and same for the node. So tag. And what is a tag? Well, it's a type def unsigned char tag, and it can be one out of at least two things. So define tag, or three things, by the way. It can be a root. Let's say we have one, and I usually put the binary representation as well. And we can have a node, a tag node, which will be 2, and that is 0010. And we can also have a tag leaf, which will be number 4, and that's 0100. And if you look at this 1, it goes to the left every time, which makes it possible to have one of these or several of these in the same variable. So this is how we is able to, if we look for a tree, for example, then we have the possibility of looking at this tag to figure out at runtime what kind of structure this is. Okay? And let's copy this into a comment so I can, or maybe we can, no, let's copy it to the comment. I think the screen is a little bit too small for split screens and stuff. Okay. So let's define a root, and we have a couple of different things here. We will have a tag, so we do dot tag equals. It's as simple as that. And what will we have here? Well, we want to have the tag root, but we do also want to have the tag node, because the root is a node after all. So let's do an OR sign right here and do tag leaf. No, tag node. So this can be either a root, or it can be a root and a node at the same time. Okay, that's tag. Then we have north, and north will simply, let's cast this to a tree and point towards itself. So we know if it points to itself, then we know it's a root. Then we have west, and west we will just initialize to 0. Same with the east. Do we have it east? No. Yeah, we do. So east equals 0. And path equals slash, like so. And then we have the tree defined without having to do it inside of a function or anything. Kinda neat. And let's, for instance, print out the address. Let's do %p for pointer, and then we will just, I think we can just say root here. Let's try it out. And let's change one thing in the make file, by the way. So where were we? Right here. I want the standard make command to compile the tree, but first do a clean, like so. Let's see what it says. Okay, that's a couple of warnings. Probably one of these that creates the rest. Let's see. Type def union utree expected blah 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 before union. Oh, I misspelled type def. So let's see. This should be in the .h. I want to have this in the on the right. Let's see, where is it? Okay, this shouldn't be here either. Def, like so. And now probably most of the warnings will have disappeared. No? Let's see. Tree has no member named tag. Ah, right. It's a little bit trickier when we have a union like that, because you see these, we need to specify the N or the L as well. So how to do that? What if we were to just do .n equals, and then we have a double of this? Will that work? Okay, that's better. Initiation of struct as node from incompatible pointer type tree. Right, we should typecast it to tree. It is tree. We should typecast it to a node. So let's see. This far it has been very easy things to fix. Like so. And let's try it again. Okay, one thing left. Warning, format expects argument of type for star, but it's a tree. Okay, we need to typecast again. A lot of typecast in this project. And this will be it will be a void like this, I think. Cannot convert to a pointer type. Well, let's do it by reference instead. There we go. And there it is. It compiled. And it runs. Okay, so now that we have defined our data structures, let's create a utility function which creates and links up one of these trees. So let's call it, I don't know, create node. And what kind of arguments do we need? Well, we need to know the parent. So let's create one of these arguments like this. And we do also need the path. So that will be an int8 pointer. And we just call it path. Like so. And in order to know, let's see. Well, we can do something like this. Assert that the parent is there, so it's not null. Let's create a pointer for the node. And let's see. We will need something with a size as well, I think. So the size variable, we can reuse that to work with the path as well, if we need to. Okay, so let's see. We need to allocate memory for this one first. So let's set n equal to, and it's going to be a node malloc size. So let's set the size to size of struct s node. And then we will zero out that structure. So let's do something like int8 and the n and the size. And we need to create this zero function as well. So the zero function will be a void function. No need to return anything. but we do need 2 arguments. And let the first be an int8 pointer. Let's call this the... it would mostly be used for strings, so let's call it str. And then we will have an int16 size as well. And we will simply loop through this string and 0 everything out. So basically like the mem set, but I want to avoid using any library functions if I can. And this is a rather simple function to write, so let's also create a int16 n. Let's initialize n to 0 and p will point towards str. And we're going to loop as soon as p dereferenced is not null. And then we'll just increase p and we'll increase n. So we will also, no, let's remove this by the way. Instead we will check if n is less than size. That's better. Okay, and for each step of the way we will simply set p to 0 and then return. Okay, so we have created our structure, we have zeroed it out. What's next? Now we need to link it up. And we have the parent specified. So we'll simply do parent. And let's see, this will be the west. So let's set this to n. So the parent's left leg will be pointing towards this new structure. And then we will initialize the fields inside of n as well. So let's see what we've got. Here is the node. I think I'm gonna copy this into a comment, make stuff a little bit easier. So let's see. We'll set the tag to tag node, and we will set north to the parent. What else do we have? We have the east, which will be 0, and then we have the path. So let's do a simple string copy, and we will need to create cast this to char, and this will be n path. And what will we copy there? It will be the path, and the size will be 255 at most. And that's it, I think. Let's just return n. So we have the tag, the uplink, the downlink, the link to the leaves, and the path. That's everything. Like so. So let's create one of these nodes and see if we can make that work. So let's create one of these pointers, and n will be equal to create node, and the first will be the parent, so let's say root, and the second, perhaps we need to reference it like this, and the second will be the path. So let's say we call this users. We will assert that n is true. Let's create an n2. And n2 will be equal to create node, and this time we will set n as the parent, and the complete path will be users login. We'll stick with the same example, and let's assert n2 as well, and then we can perhaps print the addresses of these pointers. So %p, %p, and the first is n, the second is n2, like so, and then we will free n2, and we will free n, and return 0. Let me just check through this create node function if there is anything else we need to cast. So let's see, size of n equals malloc. This size perhaps need to be a regular int. 0 ought to be okay. And yeah, looks fine. I probably forgot about something, but let's go. Oh, let's see. Create node, passing argument 1 from incompatible pointer type, expected node star, but argument is of type 3 star. That's right. We need to cast the north link as a tree. So let's just do that. Let's see, north. So this will be a tree because we're not. No, that can't be it. Which one was it? Here we go. Create node. Okay. Expected node. Right. Alright. So it's this one. Let's cast this to a node because the root is also a node, and one error should be gone. Yes. Create node user. Okay, it defaults to a char string. So let's cast this to an int 8. This is the trouble when you are using your own variable types, but I think that it has a lot of positive effects as well. Besides, you become really good at casting after a while. Now it compiled. Let's see. And we have 2 pointers and no error. It works perfectly fine. Nice. Okay, what's next? We can create our nodes. Perhaps we should create leaves then. Why not? So let's just create a leaf star, create leaf, and what arguments do we need for this one? We will need a path, or do we? We will need a key though, and we will also need a size to that key. What else? The path is included in the key, so that's nothing to worry about. We do, however, need to know the parent. So let's put the parent here as well. And that should be it, I think. Okay, so we need a node N, we need a leaf L, and no, we don't need the N. We do have the parent, so that's not really necessary. However, I want to assert that we do have a parent which is not 0. We need a key and a size. Right. Well, let's begin coding and see where it takes us. Okay, so we have the parent, so we know where the nearest node is, but it's not certain that this leaf is connected directly to its node. Perhaps there's a couple of different leaves between. So instead of creating a parent like this, I think we will have a tree, which can be a node or a leaf, and this will be on the western side of this leaf. Okay, so let's assert the west instead, and it doesn't really matter to us if that is a node or a tree. So let's create, I will create a variable for this. I'm not sure I'm going to need it, but what do we need to do? We need to be able to find the last leaf. That's a good solution, because it will look something like this. We will have a node, and then we'll have leaf 1, then we'll have leaf 2, leaf 3, and so on. So we need to find the last leaf in the chain, and if we don't find any leaf, we will connect it directly to the node. That's a good solution, I think. Okay, so let's create that utility function. So this will return a leaf, and let's call it let's let's see, find last. And do we need to give anything? Well, we need to give a parent or the nearest node. Let's call it parent. So node parent. Right. So let's assert that we have a parent, and we need a leaf L, and we need a loop looking through this chain. Perhaps we should name this find last linear, because then we can optimize it later on and have like a find last something else, and then we can just alias that through a macro. So something like this: define find last x as find last linear x, and then we can simply change this one, and we don't need to change every function that calls that function. That's a good tip. Alright, so let's do a for loop. We point L towards the let's see, towards the east of the node. So the parent east. And we will loop as long as we have an L. So let's see, when L is 0, we stop. So it's better to loop as long as L have an east. And for each step, we will set L equal to L east. So one step to the right each iteration. But this will break if we don't have any leaves. So let's check that first. So if parent east is 0, then we will simply return 0. So let's have a function for that, or a macro rather. So we don't need those, and we can just say return error, no error. And then we define a macro for that. I like macros. Define return error of x. And what do we want to do then? We are going to find the backslash somewhere. Here it is. Okay, so let's do two things. Let's change the error number to x, and then we will return, let's return a null pointer. And what is a null pointer? Thinking, do we need to define that? That should be included in C23, but I'm not really sure that they did that properly, because that should be well, an object or a variable which always should be available. There is an include file called std something. Std. Let's see. So grep ri null pointer user include and x86 something. There. Basic file. Type def, decal type, null pointer t, C++. Perhaps this is an older GCC or something. Never mind, let's do it another way. Oh, I shouldn't have closed that window. Where were I? Here, export home equals $pvd, $pvd, like that, and let's create our own null pointer instead. So let's see. Type def null point. Type def void star null pointer and null pointer equals 0. That should do it, right? Right, return null pointer. Now we can simply do ret no error. Let's also set this to 0 at the beginning, in case some library call alters it. Let's do the same here. Our number equals no error. And nothing can really go wrong here unless we supply the wrong arguments. Okay, where were we? Find last linear. We want to find the last in the chain. So for each step we don't really need to do anything. As soon as there's nothing to the east, we will break out of this loop, and then L will simply be equal to the last one. We can, however, assert, no we can, yes we can, we really do that. Let's assert that L is not 0, and then we will simply return L. Okay, so now we have a utility function that will find the last node. So let's set L equal to find last. And what do we need for it? we need the parent. So how do we find the parent? We do not have that. Tree to the west. That could be a leaf as well, right? Perhaps we should do something like node parent, or possibly grandparent. Okay, so we have the parent, the nearest node, and that's all we need, right? Yeah. Okay, so find last, and we give the parent, and we need to assert that we have a parent, and then we don't need to assert that we have west, because let's see, no. Okay, so L is equal to find last parent. So after this line we have defined the nearest no, this is the last leaf, right? So if this returns 0, then we know we are directly connected to the right. Let's just do this for now. Directly connected, and else L is a leaf. Alright. So before we do these checks, let's create this leaf. So we need another of these variables. Let's call this new, or new perhaps with an L. And let's create one for the size as well. But we have a size variable already. Let's call this count instead. That's more accurate. And this will be a size. And size will be equal to the size of a leaf, struct sLeaf, and new will be equal to a leaf casted Malloc of size. And we assert that we have this new one. And now we come to this part. So if we are directly connected to our node, then we will simply do parent east equals new. And if we're not, then we will do L, let's see, no, this is to the right, so the east, yeah, that's right, by the way. So L east equals new, like so. And now we will simply initialize the fields of the leaf. As before, I will make a comment and paste this in, because with this font size my screen isn't big enough to split. I am aware of that function though. Okay, so before we do that, by the way, let's zero out this structure. So zero out an int 8 version of new size, and the rest of the fields, let's fill them in one at a time. So we have new tag equal to tag leaf. We have a tree to the west, so new west is equal to, depending on if we did this already, right? New, no, we did the other direction. Okay. So if we don't have an L, which means we're directly connected to the node, so then we will do something like this. It will be a node of the parent. Otherwise, it will be a leaf of L, like so. And this is a ternary, kind of an if statement. Okay, what's next? New, and we have done tag west east. Then we have the key. Let's simply string copy the key. So let's make this a char, and we will use our key, this one. And we will copy, to the key, we copy our key. And how big is it? Let's do 127, so we have a little extra space, like so. And then we come to this part. So we will also have a value. So int 8 value. Like that. And let's reuse our size variable. So let's set size to the string length. No, that's not, by the way. We have a size as an argument, this count variable. We can use that instead. So what do we need to do? We need to create, let's select this, new value equals int 8 casted malloc of count bytes with 0 new value times, and then we will, let's see, we will simply string copy cast to char, and it should go to new value. Perhaps we should assert that new value was able to allocate those bytes. So new.value, and the source is also char casted, and it's named value, and how big that will be count. Okay, so what do we have? We have the tag, we have the west, we have the east, key, value, size is left. So new size equals count. Return L. And it is linked up and ready. Okay, so now we should be able to create a leaf as well. Let's see if we can do that. And before that, let's just see if it compiles. Probably have a couple of errors. It's kinda impossible not to have when doing this semi-advanced piece of code. But it should be fast enough to resolve. Expected identifier, null pointer, return, before return, so 21. This is here, let's remove this comment. And that changed the lines, of course. Let's run this again. It's still on line 21 in 3. Okay, in the H file. Do I have a yeah, I do. Okay. Line 21. Right, when we define a macro, we should end all the lines but the last one with this, and we should not have a semicolon. Alright. I hope the rest of the errors is as easy. Create node, error, no error undeclared. That's right, I did never declare those errors. And as of now, we do only have one. So define no error as 0. Like so. And size 16, that's not right. 59. 59 in the other file, 59. Right, this should be a int 16, of course. And the warning pointer type mismatch. Node parent. Pointer type mismatch in conditional expression. cast a pointer from integer. Okay, that's another error. Let's see where we had this. Okay, newest equals node parent, and parent is node. Yeah, we should probably, let's see, where were we? Here. We should do the other way around. This should be tree, and this as well. Okay, warning, cast a pointer from integer of different size. The string copy char new value, char value, strncpy. Cast a pointer from integer. How did I declare this? Int 8 value, no? Yeah, it should be a star here, okay. This should be an int 8 pointer. And new size equals count L value required as left operand of the assignment. Oh, I forgot one letter. Let's see, where were we? Find last linear, create leaf, and new arrow size. Node star n warning unused variable. Okay, 58. 58. There. Let's remove that one. And now it should compile. There we go. Great. So the troubleshooting has been very smooth and effective today. I like that. Less than 5 minutes per session, I think. Finding this editor, on the other hand. Okay, let's see. Let's test this out then. We have 2 nodes, so let's connect something. Leaf L1, L2, and L1 equal to create leaf, and I don't remember we need a parent, we need a key, a value, and a count. Okay, so parent we have key, so int 8 key and value, and we need the size as well, so int 16 size. So before we create it, let's initialize those variables. Let's say we have a key of, so we're inside /user/login, perhaps it's my user, and the value might be, let's cast this by the way to an int 8, and same here. And what should be the value? Let's just put something, some kind of hex string or something. This could be like a session cookie variable or something like that. And the size will be equal to an int 16 of string length. And what do we send? We send the char version of value. Okay, so now we create a leaf and we connect it to M2, and we need the key and the value and the size. Like so. Let's assert we have an L1. And if we do, let's print something from that L1. For example, let's just print its value. So L1 value. And let's see if, let's begin there, by the way. What did it say? Unused variable. Okay, never mind that. And let's run tree. Assertion L1 failed. Why is that? That means that this create leaf failed. Assert parent. We have a parent. Find last. New equals assert new. Turn L. 103, that's probably down in the main. Assert L1. We should have an L1. If we didn't have an L1, this function's assertions would fail, right? What are we returning? Return the L. And what is the L? Ah, right, we should not return the L, we should return the new. Of course. This is why these assertions are so necessary. Okay, this time it went through, and as you can see, we printed out the value inside of the leaf. But are we able to create another leaf hooked up to the first leaf? That's another story. So how do we do that? Let's reuse some variables. I will create another key. Let's call this John. And we will have a value, which simply will be another string, like so. And the size will be an int 16 version of the string length of the char version of value. Like so. And L2 will be equal to create leaf, and this time the, let's see, we will still reference the nearest node right here, and it will find the last leaf. So key value size, we assert L2, and if it's non-negative we will print. Let's do the key this time. So the key of L2. Let's compile. What does it say? Warning, pointer, target, and assignment. Right, I forgot to do those. So int 8 and int 8. There we go. And let's see. We get John, we get this, and no error. So everything we have coded today has worked very fine. This is as long as we can go on in this episode. It's probably a lot more than an hour anyway. If you like this episode, there will be more in this series, and I hope you can like and subscribe to the channel. And on Friday I will have a live stream where I code the networking part of the main database program in C. So if you like this one, you will like the live stream even more. I see you Friday. Thanks for watching and thanks for today.